Неговата помощта. Може ли да ползи си избавиш да дойде на кофе брейк да се разпределя на това, защото да имаме време да ви кажа.
Good morning, everybody. Let's start our morning session. It's my pleasure to introduce Anna Fino from University of Torino and Florida International University in Miami. You see the title, the talk, Canonical Metrics in Complex Geometry. You have the floor, please.
Okay, first of all, I want to thank you very much, the organizer, for the nice invitation, especially Willy. And okay, it's the first time, in fact, in Sofia, I was only going to the airport. So this time I am very happy to be here. And my talk is canonical. It's about canonical metric in complex geometry. So at the beginning, I will try to give an introduction why we want to study some sort of canonical metric. And so let's start. Let's start with the. I will try to give an idea of canonical can be everything, but let's see. Okay, so let's start with Riemannian manifold. And the natural question is, okay, can we keep M our manifold with a canonical metric? When you have a surface, a real surface in complex dimension 1 result, an important result, is every compact Riemann surface as a metric of constant Gauss curvature. So one can think, okay, this is a real dimension 2, complex dimension 1. What happened in either dimension? We will look at the complex case. Okay, one can put the same question, forget about the complex structure, and just work on Riemannian manifold, but we look in complex case. And we look in non-Kähler. In a moment, I will review what is Kähler, but in Kähler geometry, the problem becomes to find the metric with some special property for the curvature, like Kähler-Einstein, constant scalar curvature, whatever. In non-Kähler complex geometry, we see special type of metric, a meter metric, will be compatible with some central complex structure. And in particular, we will consider two types. Okay, I will give the exact definition of the two type of metric, balance and pluriclose. And essentially, we'll see the motivation for that will come also from theoretical physics. So let's start. Kähler case. Okay, we will have complex manifold. So we will have an endomorphism with square equal to minus and delta. Essentially, we will have locally complex coordinate. And we can say that the Riemannian metric is compatible with the complex structure if, in any point, if you take U and V, tiny vector, then essentially you are asking that J is an isometry, right, with respect to the metric. And so we can define in a, oh, sorry, I want to point. Okay. You can define in a natural way a true form, which is this expression. And the nice thing here that this true form is J invariant, so it's a type of one. And in fact, if you have the metric or to have this true form will be the same. Okay? We say that in Kähler geometry, what happens that this form is closed. Okay? So you have a mixture of symplectic geometry and complex geometry. And that's exactly the compatibility. And standard example of Kähler geometry are Riemann surfaces. In fact, in complex dimension 1 is always true that the Riemann surfaces are Kähler. And then we have complex toric, complex projective space, and more general projective variety, locus of homogeneous polynomials. Okay? Okay, so complex dimension 1 is easy in some sense because everything is Kähler, but already in complex dimension bigger than equal than 2, there are some topological conditions that in complex dimension 2 is also sufficient condition. That's nice because for complex surfaces we know that the manifold is scalar if and only if the first polynomial But in higher dimension, this is only a necessary condition. So we have some topological restriction. One restriction that we'll see later for other type of geometry is the formalism, in the sense of rational homogeneity. I will go back to this condition later in the non-trivial case. Okay, another nice thing, this is maybe one of the more beautiful theorems in Kähler geometry. When we have a Kähler manifold and zeta alpha are just the complex coordinate, the homomorphic coordinate, you can write the omega, the 114 that I wrote before, just locally with this expression. And the nice thing here, when you have a Kähler metric, that the rich tensor is always invariant by the complex structure, so J invariant. And since it's J invariant, symmetric tensor using J as before, we can define a 114. This 114 define the rich form, and the nice thing here that if you take 2 pi of that form, 114, this is closed. It's a 114 which is closed and represent the first chain class of the manifold. So it was conjectured by Calabi that, okay, let's start then the first chain class of our manifold, and let's take a closed 114 that represents the cohomology class, the first chain class. It's possible to find a Kähler metric, Kähler form, for which the Ricci is exactly that form. This was open for 20 years, let's say, and then Yao solved the solved the problem, and in fact he proved exactly what is called now the Calabi-Yao theorem, that if we take a Kähler manifold and we take Rotilde, which is a closed form, represent the first chain class, then there exists a unique Kähler form in the Durand class, or the original Kähler form, for which the Ricci is exactly a Rotilde. Okay, the way how we prove that essentially is to reduce the problem to a complex Monge-Ampère equation. This can be viewed, so we have a first answer to the first slides, because this can be viewed as a higher dimensional analog of the uniformization theorem, okay, that I put in the first slide. And the nice thing here is when C1 is 0. When the first chain class is 0, then there is, in this case, the metric will be Ricci flat, okay, and will be unique, and then give the case of, for the metric, holonomy in SUN, special holonomy, Ricci flat metric. So there was a lot of interest to try to extend the Yao theorem in non-Kähler setting. We will see one way. One way is what is called Hall or Strominger system. That's a way, and this will be related to one of the 2 types of metric that I mentioned from the beginning, the balance. Okay, but to go, so now we'll go to non-Kähler. Non-Kähler. So we will tweak some of the hypotheses that we have in Kähler case, Calabi-Yao case. And let's talk about Calabi-Yao in, let's say, in complex case, in non-Kähler. Kähler and non-Kähler. What does it mean? Let's start with a compound, now only complex manifold. Can be Kähler or not, it doesn't matter. We say that it's Calabi-Yao if the canonical bundle is holomorphically trivial. What does it mean? It means that if the complex dimension is n, then you have an n0 form which is never vanishing on your manifold. So it's the canonical bundle is trivial. This has been studied a lot after Yao solution to the Calabi conjecture. Okay, so this helps us to put the question I wrote at the beginning. Which canonical Newton metric one can choose on a compound non-Kähler Calabi-Yao manifold? Okay, we'll see that one possible choice of metric is what is called conformal balance. Okay, so that means that if you work in the conform, if you do a conformal change in your metric, you get a balance metric. In a moment we'll see does it mean balance? Essentially, instead of asking that the one form is closed, you will ask that it is co-closed. Okay? And we'll see that the motivation to study that metric comes again by Calabi-Yau theorem, because Calabi-Yau theorem can be generalized to what is called whole-Schrödinger system. And this is the first link in physics, in the sense that usual Calabi-Yau metric can be used as a solution of that system. So let's start with this, what they call balance metric. Okay, what is the definition of balance metric? So it's a meter metric. We have our complex manifold of complete dimension n, and what we are asking essentially is that omega, as I say, is co-closed. That means if you take the wedge product of your omega n minus 1 times, this is just closed. There are it's quite rich, the literature about balance metric. One nice characterization is due to Duchamp, just in terms of Laplacian, because he proved that a metric, a meter metric, is balanced if you take this Laplacian, so you have D, which is the composable del, that's the bar. You just say the Laplacian with respect del, Laplacian with respect to the bar, and the usual Laplacian. And then you have this equality. So are all correlated by that equality for every function on M with value in C. But the nicer characterization is due to Michelson. In fact, she was maybe the first one probably that she studied more this balance condition. And she proved that she proved a result using the duality between forms and currents. Because she showed that compact complex manifold as a balance metric, if you don't leave, you have that condition in terms of currents, so it cannot be any positive currents. You have the notion of positive currents like positive forms by duality of degree 1, 1, which are components of boundary. What does it mean? That the currents cannot be written as d of some other currents plus the bar of the cannula, that current. Okay, you have d bar by duality also of currents. This looks very, let's say, abstract characterization of balance, but it's very useful because using currents, you can find the easy obstruction on a compact complex manifold to admit or not complex structure. Because one obstruction is that if you take every compact manifold of codimension 1, this has to be homologous to 0. If you have that's one obstruction for the existence of balance. And this obstruction, this is the only one. I mean, there are not so many obstructions for compact complex manifold on such metric. And this can be applied, for instance, in the case of Calabi-Ekman manifold. With a Calabi-Ekman manifold are product of odd dimension sphere. So in that case, you cannot have balance metric. Okay, this is our characterization. What are examples? One of the nicer example, here we have many experts here about twistor space, is a twistor space of a 4-dimensional oriented anti-set dual in mathematics. So anti-set dual, the W plus part of the Y tensor is vanishing, and you are taking essentially the bundle of compatible, orientable, oriented almost complete structure on your form manifold, and this is due to Michelson and Duchamp independently. But the nice thing, and this go back to the Kähler geometry, if you apply a beam meromorphism to a Kähler manifold, the Kähler condition is not anymore preserved, but is preserved the balance condition. And that's a nice result due to Alessandrini and Bassanelli. So we start with Kähler and we go to balance. And there are two types of classes that are quite interesting. Are the Moisson manifold, both are just obtained by bibliomorphy from compact projective manifold. So you start with projective compact manifold and then you just apply bibliomorphy, and more general the Fuji class. These are again just bibliomorphy to compact manifold. But there is a very simple example that was shown by Abena and Grossi. Just take a complex group. So you have a complex structure which is simple by bottom, and just take any left environment compartment with that. Then you get a balanced manifold. This is non-compact, but if you take just a compact portion by a lattice of your complex, you get compact manifold. But there is another type, geometric construction that give you balance metric. This is due to Li, Fu, and Yao. And is applying conical transition. I don't want to explain what are conical transition in a few minutes, but anyway, what you are doing is you are essentially blow up some rational curves, let's say, then doing some sort of deformations and smoothing to get smooth complex manifold. But then the nice thing here, that you start from some killer and you go again to balance, and also with canonical, the holomorphic canonical bundle is trivial. One nice thing here of this result, that if you take the connected sum of S3 cross S3, this is balance, okay? But it's still open, for instance, the case S3 cross S3. I mean, if you take a complex structure for which you have the Calabi-Ekman, then we know it cannot have balance. But S3 cross S3 without that complex structure, we don't know. There are only partial results. So this is a very simple problem. Okay, simple to say, but not simple to solve. Then there is a result by Jusim for the sum, quite recent, where they consider the non-compact case. So they consider non-compact simply groups of inner type. This inner type is related to the symmetric pair, essentially, associated to the group. And then they show that these always, if you take an invariant complex structure, that they always have a compatible balance. So it's quite rich in that case. And you can again, considering a lattice, co-compact, that is crystal group, you can again construct compact manifold. Okay, let's see. I will present now some recent results that we did with Angelo and Misha Lepisky to construct new compact balance manifold with a simple construction. This is the construction not yet adapted to the complex case, so it's general, just topological, right? We start with manifold and the diffeomorphism, and we just consider what is called the mapping torus or suspension. What is? You just take M, your manifold, times the interval, 0, 1, and you identify the point 0 with using the diffeomorphy with F 1, okay? So we have a natural reaction from M times the interval to the interval, and that natural reaction gives you bundle structure, smooth fiber bundle of over S1 with fiber the manifold, the starting manifold, you have diffeomorphy. What is nice here that the structure group of the bundle 1/4. There is this nice theorem due to Tischler. They show that is if and only if. So every time you have a kappa manifold, this is a mapping torus. If and only if you have a non-vanishing closed 1/4. In this class, for instance, belong real manifold and Sol manifold. What are just, so you're taking G, a Lie group, simply connect Lie group, which is other nilpotent or solvable, and you just quotient by lattice. That's belong to this class, both of them. Okay, before to present the result, I just see somewhat what happened if we consider then a Sol manifold, a composite manifold. What happened for the existence of balance structure in one special case, the space that the complex structure J is invariant. What does mean invariant? Means that it's coming from a complex structure on the Lie algebra, G. And the nice thing here, just using a symmetrization, that if you ask for a balance metric, even the non-invariant one, you always, if you have a non-invariant one, you get an invariant one, just by symmetrization. So everything can be studied, let's say, at the level of Lie algebra. And there are some known results in dimension 6. I didn't mention, but of course, this balance condition for complex dimension 2 is just a Kähler condition. So the first dimension for which is interested in this type of geometry is complex dimension, at least 3. In the reported case, there is a classification due to Ugarte. Then in a paper with Otale and Ugarte, we consider a more general condition that unimodular. So this is the necessary condition by Billner to have the compact quotient solvable. And then we ask that you have a holomorphic 304, which is very close to the Calabi-Yau condition. And we classify that in a paper with Otale and Ugarte. And more recently, I consider with my PhD student, Paradiso, another class of solvable Lie groups, almost abelian and almost nilpotent. The almost nilpotent case is almost finished, the dimension 6. Okay, what does mean almost abelian? Is almost abelian in the sense it's not abelian, but what you have something like a semi-direct product R times an abelian. Okay. When I say time, it's a semi-direct product, let's say. But there is also a nice recent construction due to Freiberg's one, which is called share construction. This is a generalization of group action, let's say. And the nice thing of that construction, that is preserving the balance stuff. So if you start with balance and you apply that construction, then the balance condition is preserved. Okay, let's go to the complex case. The motivation so we introduce a sort of, let's say, suspension adapted to the complex case in order to have a balance metric. And the motivation comes from construction due to Queen and Wang, where they construct 6-dimensional compact manifold, which are at the same time complex Calabi-Yau, in the sense that I explained before, and also, I don't want to do that, and also symplectic Calabi-Yau. What does mean symplectic Calabi-Yau? You have a symplectic structure, you have an almost complex structure, and then you can define the first-chain class associated to the almost complex structure, and you are asking that C1 is 0. So this is the level, we don't have metric here, right? And so the natural question is which type of metric you can have compatible with the complex structure. And so the problem that we study is, okay, can we have balance metric there? And the answer will be yes. I will explain a little bit that construction, because it's nice, it's coming from, again, Kähler geometry, in particular hyperkähler geometry. Okay, so what he used this construction, then we'll see how we generalize that, is we start with the Kummer surface. What is the Kummer surface? It's very simple. You just you solve the singularity the quotient of the two torus, okay, over what? This involution, which is just given by multiplication by minus 1. Okay, you have your 16 isolated dipole point, and then you blow up, solve the singularity. But you can describe also your Kummer surface in this way. You just blow up T2 in the two torus in any point, and you quotient by the involution induced by sigma. Okay, what we have, that the fixed point of this involution is just the union of the sectional divisor over all singularity, and there is a natural way to define a holomorphic 204 on your comment. You just take the standard 204, and this zeta 1, which is zeta 2, and this is used in over vanishing 204 on the two torus, and then pull back, and you get something on the comment. So what we have? We have Kähler, Ricci flat, and we have also holomorphic 204, right here. So we have hyperkähler. Okay, now let's take a matrix, 2 times 2, with determinant 1, and we coefficient in zeta plus I zeta. And then we suppose this condition. This condition is geometric, in fact. We'll see later why. We have this condition that the trace, modulo the trace of A is bigger than 2, diagonalizable with these eigenvalues, lambda and the inverse of lambda, of course, because determinant 1. And let's denote by dv1, dv2, the eigenvector, okay? The induced map that you have in cohomology. What happened? That map preserve our two form, d1 which dv2, and okay, also the divisor, which is the union of vi, the sectional divisor. So we have a holomorphic transformation. Be careful that it's only preserving the complex structure and the holomorphic G204, but it's not preserving the Kähler metric. Okay, it's only at the level of complex stuff. We preserve the holomorphic 204. And then one can take the zeta action, very simple, in this way, okay, on the product of the two torus R and S1, just using A. Here the transaction, and here nothing, okay? So we will have a natural action, what? This nothing here will give this factor S1, and then we will have something on the Kummer times R. The quotient is exactly the manifold that they get in their construction, the Queen-Wang that I mentioned before, and I will denote by this notation A, Km, and that's trivial canonical law again. So it's complex canonical. Okay, how we can work on that, generalize on that? What we know? We know the following. We can define, so let's say we have a compact Kähler manifold, now here in n dimension, and let's say K holomorphic automorphic. So it's only preserving the complex structure. We say that this is hyperbolic if the action, the induced action of the automorphism F on cohomology, on real cohomology, as a unique eigenvector, okay? And then you have the condition lambda bigger than 1. This is related to the condition that I considered before in the special example. Okay, now what we can do? Okay, we have this hyperbolic automorphism of the compact Kähler, and let's take a lattice in C generated by C1, G2, these two vectors. And we can define what we call hyperbolic torus of space. We can do this more general for more diffeomorphy, but I will explain this in this special case with only one. We call hyperbolic torus suspension associated to the pair, so we need two diffeomorphy here with a PS, and the other one is just identity on M. And then we take the quotient, okay, by zeta 2. The quotient is the following. So you see, it's just, again, you just work here like a suspension, and you get S1 here, because here we are essentially one of the two factors, we are doing nothing. And so we get a new manifold, complex manifold, which is diffeomorphic to the mapping torus of M times S1. And that the previous construction was just a special case for this field. Okay, but the previous construction was also using holomorphic 204. So what we will ask here is to start with a compact hyperkähler. So we will have Kähler and the holomorphically symplectic structure. So holomorphic M0 form essentially. And let's take a hyperbolic automorphism in the sense before we preserve also the holomorphic symplectic form. Then one can construct what we'll call hyperbolic holomorphically symplectic suspension. We proved in a recent result that this manifold obtained this way is, as always, a balanced metric. This is an existing result. Okay? And so in particular the previous example, starting from Kummer, as a balanced metric. I will not say anything, almost nothing about the proof. Is a little bit not technical, because at the end we use essentially the Michelson characterization. So it's an existing result using currents. And we use the fact that you have a natural projection here, right? Remember that, maybe not, but this SF is the product of a mapping torus. So you have a projection over S1 times S1. So you have a natural projection on a complex curve, elliptic curve in this case. And essentially we use that condition that this map in the Michelson language is essential, but I don't want to talk about it. I want to say something here, because I mentioned solid manifold before, and in fact one can get solid manifold also with this type of construction. We just start with the real four torus, and we just apply A. A is a matrix like before, exactly in the same way. If you apply the previous construction, then the suspension, what you get is a solid manifold, which is almost abelian. And here the method is explicit, because, okay, it's a solid manifold, right? So you write everything in the left one. Okay, so one problem that we are working now, we'll see also later why, is to find, okay, we have an existing result, but can we find an explicit balance metric? Can we write an explicit metric? I will go back to this, why we want a metric. Okay, I think now it's time. I mentioned at the beginning how Schrödinger system, and that was related to Calabi-Yau theorem. Okay, this is related to physics in the sense that is the geometry of compactification of heterotic superstrings with torsion. This doesn't mean nothing for the moment, but essentially you have a link from 10 dimension to 4 dimension, which is a Minkowski space. And so our 10 dimension as a Lorentzian metric, okay, this is one of the bosonic object that you have in your model. And this manifold is locally a product of Minkowski space times compact sigma manifold. The geometry that you have in this six manifold is related to what I said before, because in fact, we'll see in a moment, and that you have a special type of complex geometry there, and we have also gauge bundle, vector bundle, which will be holomorphic over the six manifold. So the idea here, roughly speaking, is to, okay, look the geometry that comes for superstring theory and see what type of geometry you have in six manifold and six, and on the holomorphic vector bundle. And the answer to this was given by independently by Hall and Schrödinger. And essentially the interest comes by this first result, because, okay, your metric that you have in the product, Minkowski times M6, can have two types of metrics, other than just the product metric or the Warpy product metric. If you have the product metric, like this, then you are essentially in terms of connection, gate connection, you are just considering the spin connection on the tangent bundle of M6. And the nice thing here, that your manifold Calabi conjecture, because your 6 manifold must be a Calabi-Yau with Killer-Ricci flat. Okay? But what Hall and Strominger generalized a little bit that, considering what happens if we have a warpy product. Okay? In this case, we get what is known. In a moment, I will review the equation as a Hall-Strominger system. In this case, the manifold, like before, is not anymore Keller, not necessarily Keller. General is not Keller in this case. The Keller case is a special solution of special case, and will be Calabi-Yau complex in the sense that I described at the beginning. So the canonical bundle is trivial. Okay, let's go to the system. Okay, so we are in compass dimension free. We have a nowhere vanishing holomorphic free zero form. Canonical bundle is holomorphically trivial. Complex Calabi-Yau in the sense that I said before. And we have a complex vector bundle on our manifold with an Hermitian metric along the fiber. And then we have some data, alpha prime, which is a constant. This from physics point of view is a sign, but in mathematics you can consider also both signs. Okay, let's say is negative anyway. The physics good thing that you should have. But we'll see in a moment that the case that we consider is in fact in physics not solving all the equations from physics, but mathematically is giving nice property. So what are the equations? Okay, here we have essentially two connections. One is a chain connection in the holomorphic bundle, and the other one is a metric connection. Okay, any connection preserving the metric and the complex structure. We'll see in a moment why one makes sense from physics point of view and the other not much. Anyway, the conditions are the following. So we denote by R nabla and FH the curvature. So here I am taking trace. So I am viewing the curvature as two forms with value and endomorphism. Okay? In the case of FH, we value an endomorphism of E. In the case of nabla, two forms with value just in the endomorphism of the T10, the 10. So the first equation are called also Hermitian-Young-Mills equation, right? Because essentially it's a condition for which E is polystable. Okay, that's a condition. So we have a condition of curvature. The second condition is the conformal balance condition, right? Because in general, this is just the norm of the free zero form with respect to the metric. In the Keller case, this is, you can see when d omega is 0, this gives you this constant, right? So you give Ricci flat. But we are interested in the case when this is not constant. So what you're doing is just a conformal change. And the third equation, which is more difficult to solve, what is called the Bianchi identity, you see is involving this form, dt bar of the one form. This is like the torsion of the geometric structure that you have as a free structure. And you see, this is exactly the curvature condition, let's say, right? In the Calabi-Yau case, you have, okay, let's take one form, and you ask for the Ricci form of the metric. Here you have a combination of the curvature, is the same. So in that case, in this case, it's canonical, okay? You have a condition on curvature. In that case, so you have instead of working with one form, you work with close to two form, and you ask this condition on the curvature. And I explain here why Calabi-Yau manifold. I explained already before a special case, but in non-Keller case, you have a choice. You have many. In fact, Baudouchon showed that you have one parameter family of natural Hermitian connection that you can choose. And okay, we can choose, for instance, the Chern connection, which the one part of the torsion is vanished, or the Bismuth connection. which is the unique match connection, the complex structure with torsion skew symmetric in all the argument. For the moment, we'll consider the chain connection. Okay, of course, the first thinking was to find solutions that were non-killer to help solve the system. And the first non-killer solution was given by Fu and Yao, and the idea were considering K-free surfaces and toric fibration over K-free surfaces. So they were using more a general construction with the Goldstein and Pushing that offered torus fibration or morphic fibration over complex essentially surfaces that in this case are K-free surfaces. There are also other type of solution here. I mentioned some results on Lie groups and quotients, and also solution on non-killer fibration over K-free surfaces due to Garcia Fernandez. There is a lot of now literature about that. More recently by Fay, Wang, and Picard, they consider this nice fibration where the fiber is a compact hyperkiller, and here the base is just a compact Riemann surface with this condition on the G. But let's go to the Goldstein sheet and let's see how we can generalize that. Okay, so we start with a K-free surface. We reach a flat killer metric. And let's say we need a T2 bundle, right? So we need, let's say, two 1-1 forms, which are anti-dual, which represent integer classes. Here, I should put 2 pi, but I forget about that, okay? And we can take the toric fibration, essentially considering the connection one form such that the differential of that form is the pullback, okay? So we are considering the complex structure here, essentially on M, we make this projection holomorphic. So if you just do that like that, you take the pullback of the 2-0 form here, and you just consider as a vertical part, theta, which theta 1, then you get a balance method. What they did for Yao is to modify this part. So they essentially, instead of considering, you see, before it was a pullback of omega s, here you just multiply that by a scalar function, and then you can reduce the condition for, let's say, you can ask again, what is the condition to have balance? It's a balance metric, this is not a problem. But the more difficult part is to impose a third equation that we had from the system, and then reduce to a motion pair, complex motion pair equation, again. This is essentially just a condition for the metric, and they could solve. I mean, it's not easy stuff, but you can, essentially, the very nice idea is here is this modification to modify these ansatz. And also, of course, it's very hard to show that you have a solution. That's the analytic part. Okay, what in the result? Recent result with Granchero and then Sony, what we did. Okay, I will not present what all we did, but just the idea was, okay, to replace a K-free, smooth K-free surfaces with K-free ordinary form. Okay, so we allow some singularity. The type of singularity are cyclic singularity, and in this way, we generalize the previous theorem by Fu and Yao in that setting, and we found our new solution for the Hall-Ströminger. The nice thing here, that okay, this is not simply connected, right? But this one, if you take the connected sum of S2 times S4, connected sum R plus 1, S3 cross S3, which is simply connected, gives a new solution to Hall-Ströminger. And the case K equal to 22 or 22 gives exactly the Fu-Yao solution. Good. And essentially to construct that we use safer as one bundle, essentially. But I don't want to talk about that, but just to give an idea what is going on. So we consider essentially two rational divisors on the orbital, and then using that, we can go first to the first safer as one bundle, and then taking a S1 bundle over there. That one is moved, and so we have a T2 bundle over our orbital. Okay, in the last minute, I want to mention at the beginning I mentioned balance and also pluriclose, but I didn't define pluriclose. Okay, this is just the Bismuth connection that I mentioned before. So maybe now you can see why the condition that I said before, the torsion is Q-symmetric in all the argument, and the torsion is determining the connection, the Bismuth connection, because the torsion is just DC of the 114 here. Okay, DC is just the operator given by that. And what is pluriclose? Pluriclose is just a condition that you ask that the torsion is closed. So that torsion, free form, is closed, and the equivalent is just to ask DD bar. That omega is DD bar closed instead of DD closed. This is for n equal to 2 is a special case of what is called Goudouchon metric. And for n equal to 2, due to result to Goudouchon, you always have, in any compact complex surface, you always have a pluriclose metric, just in the conformal change. So again, the interesting case here is complex dimension because it's 2, from the existent point of view. Example, there are many examples now. For example, the more simple example are just the real groups with the Summerson complex structure. There are many results on company manifold, compasson manifold now. And there is also a nice result that is related to the construction before of torus bundle due to Grancharov, the two Grancharov manifold, and more recent result by Potter and Tagore. I want to mention here, maybe I stop here, I prepared more, but not so much. This conjecture, the quick conjecture with Bezzoni, because if you combine balance and pluriclose, then it's scalar. This is a result due to Alexandro Ivanov, and more recently with different techniques by Popovich. So one can ask the same question. Okay, let's start with complex manifold. So the complex structure is fixed. And suppose that you have a balance metric and also a pluriclose metric at the same time, or different, of course. Then the conjecture is scalar. And in fact, this is true. Also, the example that the construction, the recent construction that I mentioned before, the hyperbolic hyperkähler construction, we were able to show that they are balanced, but they cannot make pluriclose metric. This is using again curves. Right? So for the moment, it's still open, all the compounds. So this is a nice, I think, question to see. It's not clear why. Maybe there are some obstructions. There is recently some paper by Popovich where he considered some functional, right, to look at that. In the non-compact case, this is not anymore true. Because recently, Freiberg's one constructed something on solid group, which do not admit any compact quotient. So really non-compact. They don't give compact example. Okay, I think I am over time. I am okay. I am okay. There was another part, but I will stop here. I think it's enough. So thank you very much for the attention. Not too much technical, I don't.
Any questions, Claire?
Yes?
I have two more quick questions.
Yes.
Just to see if there is a relation between this all-dimensional case and hyperdimensional case with all-dimensional case, like what happens in Arnold's quantum geometry. You ask to be practically a hypersurface in a Kähler manifold. it can be transferred
Yes.
some properties to hypersurface, which is ordination.
For I didn't mention, but for instance, for the pluricloth, we look with Marisa Fernandez and Luis Ugarte. We study when, for instance, you start with multi-dimensional manifold, like almost metric, almost contact, let's say, and then we look, for instance, when the S1 bundle has such type of structure. So in that case, you have also for the cone metric, whatever. Yes, there are results.
Okay.
Yes.
I have another question. Is it possible to obtain such a balanced method from a variational principle, like a critical point in a certain class?
Yeah, you can. Okay, there is. This is related to, for instance, a result by Bedulli and Bezzoni, where they generalize the Calabi flow for balance flow, and then you look for a functional. But it's very, let's say, that's the only geometric flow that is preserved in the balance metric, and something should be done, because it's true that is evolving, you have this functional, but it's very complicated, because it's involving some Laplacian related motion. I think it should be some other functional that is nicer. For instance, Popovic put in archive recently a functional that gives some relation also with balance, because it's trying to solve the conjecture that they mentioned. So he introduced two types of functional. One, let's say, preserving the related to the pluricloth condition, and the other one related to the balance condition. So in that case, it's considered also functional.
Okay. In general case, you have while tensor field, Bachmann tensor field, whose annulation gives you a geometrical condition.
Yes.
Is it the same?
Here, what would be the same? I mean,
for conformal balance.
For conformal balance. There are some results that are more related to the Ricci tensor or the bismuth connection, because what play role of the Ricci is a connection is the bismuth connection. Okay. So in that case, there are results. For example, one is Ricci flat, the bismuth connection.
And my last question.
Oh, many questions.
Later in the coffee break. In fact, you gave a nice result concerning TM, the total space of the tangent bundle. But for certain cases, is it a general result saying that, look, if we have this structure on the manifold, if and only if we obtain a similar structure on the total space of the tangent bundle by taking, for instance, comparative or Sasaki metric?
The only result that they know, I mean, there are results that are always on total space, and the fiber is always the torus. That's the result.
Yeah.
Yes. In more general case, I don't think that there is some. There is a result about pluricloth in the what they call project-wise bundle, for instance. That's a little bit different overall of manifold, but no other.
But there is a torus play a nice role here because it's parallelism, or why?
No, because it's from the base. If you start from the base, it's very easy then to use the metric to the base and lift.
Yeah,
and that's so it's a natural way to have a balance, because in general, to check this balance condition, unless you have, for instance, another case, we show that there exists magic. Yeah. Because in some sense, the type of vibration was nice compared with the complex structure. That's something that you did. Right? So you can generalize, but you have to be careful always with the complex structure, because otherwise, if you leave something from the base, you need to leave, right? Or you want to leave.
But that's done for the total space of the tangent bundle. So complex structure from the base manifold is...
Oh yes, that's true. That's true. Maybe synthesis. I never studied that case, but could be.
Thank you very much.
Other questions?
Johan, I have a question. If you are not so tired.
No, I am okay.
First, how do you check this conjecture for the known examples? General idea about this.
Oh no, there are many results. For instance, twist of space, Misha-Verbitsky shows if you have a twist of space and
No, I mean, what is the general idea? You use some topological abstractions
Yeah.
or?
Many time, for instance, twist of space, you use coherence. For hyperbolic, you use, because you have a characterization like the one in the killer case for pluriclose, for the system pluriclose. So for homogeneous example, let's say you use just, you reduce, if the complex structure is in Yn, you reduce everything at the level of
Yeah.
If it's not that case, the technique is always, let's say, coherence. The technique that you use is always coherence, because it's not easy to check. But all example, every time we found there is this is a balanced example, nice. Boom, there is no pluricle. Like the Fuyao construction, right? Disconnecting sum of S3 close S3 that they mentioned, they are balanced.
Yeah.
But in that case, they cannot have a pluricle. That's easy, because they satisfy the Didipol lemma. So if you have Didipol lemma plus that, then if you put that. But it's always, as you say, some general argument, either Didipol lemma or coherence. It would be nice if we find something topological or different.
That's why I
Popovich is now looking all these functions.
I wanted also to ask you if there are some topological abstractions for existence of balance or no hope to have such.
There are not really, because maybe there is more for the pluriclose case.
I see.
For balance case, no, because the variety of manifold that you have are so many.
So in general, no hope to
No, I don't think. What I am trying to do, I mean, it's wrong, I don't know, is to see with geometric flow condition. Because maybe if we found out a way to flow on the same time balance and pluriclose, then in the limit you can show something about color. This is related to the question.
Yes. Okay, thank you.
Well,
Last question. If not, let's
you say so much. Thank you for the attention. I hope that it didn't sleep so much. I try to wake up.
coffee break, you will start 11.
Thank you. I am
Okay, let's start. Our next speaker is Mirjana Đorić from University of Belgrade. The title of the talk is Geometry of Some Manifold of Riemannian Manifolds.
Thank you.
Please, you have the floor.
Thank you. I would like first to thank Professor Milusha for the kind invitation. And there is some maybe symbolic in this visit, because my first talk was in Smolja in 1986. So when Professor Ivanov was also, it was his first conference, I gave a talk there. So I'm not involved at all with women in mathematics, although I admit that I was invited several times, since my both daughters finished a PhD in mathematics and are still in science. They live in Berlin and doing mathematics. So we are somehow interesting family for women in mathematics, and but they are more so they give some interviews, and people are interested in such a family. Although you will not recognize them, because my family name is not the same as theirs. Doesn't matter if I write DJ or D with a bar, which made problems last week with my airplane. So I tried to, as Sofia said yesterday, to polish my slides. I don't know if I succeeded, and I tried to make it somehow acceptable by people who are not doing exactly differential geometry. So my field is of research is differential geometry, and especially geometry of submanifolds. So some people say that the first starts are even from the 17th century with the works of Fermat and Descartes, where curvilinear coordinates were introduced. And I think that maybe it's better to say that Leibniz and Newton gave something interesting, having in mind the differential calculus they invented. So in differential geometry we use techniques of differential calculus, and also the people I met 2 weeks ago, a professor who calls this elementary course, which we usually call geometry of curves and surfaces, he calls this course Gauss geometry, because Gauss was the first one who initiated the modern differential geometry, and actually for curves and surfaces in R3 it's enough to use the works from scientists from Gauss time. He made use of these curvilinear coordinates to describe surfaces, and his work was revolutionary, having in mind his theorem egregium, which says that curvature, which calls his name Gauss curvature, is in the intrinsic invariant, so that reminds people to go in this direction, and then Riemann made the definition of manifolds, and it went in that direction after that. What I'm doing, as I said, is the differential geometry of submanifolds, and especially it is interesting when you talk to broader public that you study geodesics or minimal surfaces, because they have many applications. Besides the mathematical theories, in the theory of complex variables, calculus of variations, topology, there are many applications in the investigation of DNA structure, since it has a double helix in it, also in molecular biology, then genetic engineering, and not only the submanifolds of Riemannian geometry, but also submanifolds of pseudo-Riemannian, but I will talk only about Riemannian geometry today. What you can find in Wikipedia is that it's that has many applications, and one of the most famous applications is the calculus that Albert Einstein used in theory of general relativity. Also, it's written on Wikipedia that outside of physics, which is quite natural, and biology that this can be used, it can be used in chemistry, economics, engineering, computer graphics, and so on, and in machine learning. For that reason, I tried to write several books where you can explicitly see that the differential geometry is applied. So it's differential geometry in physics. And these two books are, part one is manifolds, Lie groups, and Hamiltonian systems, and part two is a little bit more complicated, Fargo bundles, topology, and gauge fields, both are published by Springer, and it's for physicists. Also in computer science, which is nowadays interesting, it's, for example, in applications in algorithmic advances, computer visions, machine learning and statistics, as I said. Also you can find books especially written for engineers. It's called, for example, Introduction to Differential Geometry for Engineers. There are some older books, but also quite recent published books. Also in biology, it is interesting, since we had yesterday nice talks, that there is a differential geometry of proteins and its applications to structure determination, also to molecular genetics or for protein folding. In economics, I really don't know how I could use my computations. Usually people from physics ask me, and that is why I will try to today to show some of results in low dimensions, because usually what I did in the past is always n-dimensional. So let us have n-dimensional manifold or n plus k dimensional manifold with n-dimensional submanifold, and blah blah blah. I have this theorem, that theorem, and then physicists always write some questions about applications. That's why I wrote this. I don't know how you can write applications of differential geometry to econometrics, but maybe I will have time sometimes to read this. And I found this because I visited 10 days ago the Lund University and Professor Gudmundsson, and on his website he has bigger list of these applications of differential geometry, which I find very useful because I didn't know for all these books where differential geometry appears. So this is the, don't have time to advertise more the influence of differential geometry, especially of submanifolds, because it's now a special direction, so different from. I'm grateful to Anna because she made some introduction which I will also use, so I will skip my formula. But what I'm doing especially is the geometry of submanifolds. So the well-known name which appears is John Nash, because he studied the problem of embedding any Riemannian manifold into Euclidean space, because that was the old problem studied for 100 years before him, but it was solved locally and under some conditions, and also the codimension was much bigger than the one he obtained. So he really wrote the theorem which proved the theorem which is nowadays called the Nash embedding theorem. There are two of these theorems, and the second one, which is more famous, is published in 1956, and unfortunately this is a theorem, sorry, so that every compact, I write it only for compact case, can be embedded in a small portion of, as a small portion of this dimension. Gromov wrote this, that it is one of the main achievements of mathematics of the 20th century. In 2016 he wrote one paper about his work. Unfortunately, Nash with his wife died in 2015 in a crash accident coming back from he obtained the Abel Prize, and then it was a car accident, very famous, well known, sorry, and that's why they wrote a year after that this article. Mensch is also one of he's the only one who obtained the Nobel Prize and Abel Prize, but he obtained the Nobel Prize in 1994 for economics. So he had many different papers, and the Abel Prize he obtained for his achievements in mathematics. It is a very, very well-known movie, Beautiful Mind, from 2001, about his life and his illness, which is interesting for some people. I mentioned him because he's the best-known man who mentioned submanifolds and who gave somehow the chance to other people to say that it is important to study submanifolds, because then we know every manifold, because it can be embedded in Euclidean space. But the problem is that the codimension is big. So I will show today some results which are a kind of generalization of results from real hypersurface case, because around the 1970s many results were obtained for real hypersurfaces, and so it was after that it was difficult to find anything to prove having in mind the complex and compact structure. And so what I did with my co-author, Professor Okumura, we generalized it to so-called CR submanifolds, which is the title of today's lecture. And we studied especially CR submanifolds of maximum CR dimension. The others is difficult to control. So when we tried to study, for example, as a special case, submanifolds of codimension 2, it was even difficult. So it is very difficult when you have the dimension which I showed, 1/2, and I forgot, 2n plus 11, something like that. So it is a nice theorem, but for applications in computations it's almost impossible, because even when you have two normals, we have some results about this which I will not show today, but it is difficult to control codimension which is bigger.
But sorry, is this optimal, the dimension?
No, you can later, yes, but this one is somehow, well, what I chose.
That was the first probably.
That was the best in some case about restrictions. So there were Whitney theorem and many others. But also later they made some better. But the problem is that computations you cannot use. But the idea that you can embed this into Euclidean space, and in Euclidean space you know how to compute, it is a nice, interesting idea. But
because usually they, like for the Stein manifolds, you remember the embedding of a Stein manifold in CN, let's say, they have something like an optimal dimension.
Yes.
So thank you very much.
Yes.
Sorry.
Also, this is old result. This is, as I said, the first one is from 1953, and this one is from 1956. So after that, people also worked on this. This he did on MIT when he was a guest. He just asked for some problem, but actually he got ill after he started to do coding theory, cryptography and coding theory. Then he was ill for 25 years. He did not do anything. So what is the problems that I studied sometimes, or that I studied, that I will try today to show the results, although I have some other kind, is to classify submanifolds according to some given geometric data. So to propose some condition. For example, to be minimal, to be totally geodesic, some geometric condition, and then try to classify this kind of submanifolds according to this data and the ambient manifold. What I will, for example, what I chose today is some results connected with the second fundamental form. Since the structure of submanifold is in some sense encoded in it, or which is equivalent in the shape operator, so these are two equivalent things. So what I said is I will show you that besides the second fundamental form, which we denote by H, there is also another structure, F, which I will show soon, We consider some results, we consider some conditions which are imposed on the second fundamental form and on this structure. This is kind of, also I will study contact CRSA manifolds of a 7-dimensional sphere because I want to show some low-dimensional cases. This, although we have some results on the nearly KL6 sphere, which I just mentioned to Anna because she mentioned 6 dimension is really very interesting. Also 7-dimensional sphere is also very interesting because of these calibration problems and so on. So if a manifold is ended with the geometric structure, we have more opportunities to explore its geometric properties. On the other hand, we lose some properties because you cannot put on every manifold every geometric structure. For example, if you want to put complex structure, the manifold has to be even dimensional, for contact has to be odd, and of course more restrictions later. Also for the series of manifolds, it is important to stress that we study relation between intrinsic and extrinsic geometry. And we studied these invariants, which I tried to somehow give the basic definition so that you can have insight of my work. For example, it's well known that in 3-dimensional real space, so the one I mentioned Gauss did, there are 2 important curvature invariants. It's Gauss curvature and mean curvature. And it is well known, as I mentioned, that the Gauss curvature is intrinsic invariant. So it first was defined using the embedding in R3, so as a product of principal curvatures, which are defined using the normal, so the ambient space. And then in his theorem, Gauss showed that it does not depend on the extrinsic invariance, that it is intrinsic, which means it depends only on the metric on the surface. So at this moment I am doing a very elementary master thesis with one young colleague who should become a professor, a teacher in secondary school. So measuring the circumference of a circle on various surfaces, you can decide if you are in a flat, in a plane, or you are on a ball. So what she did is an experiment. She took one melon and she made the circle. And if you measure the circumference of a circle, it is not toward pi. It is bigger. So measuring also there is a formula. It is old from 18 something. Yeah, the theorem. Measuring also the area of a circle, you can decide from this area if you are on a plane or a surface of a positive Gauss curvature or on a surface of negative Gauss curvature. There is a formula already old. So also this is some slide from the COVID situation where you could follow many conferences online. And since I know this person here, I followed some lecture, and this is the application. So this here is a mean curvature, which I mentioned on the previous slide, and this K is the Gauss curvature. So what they do is they approximate a membrane with the surface, so it is with the sphere, sorry, and then the curvature of the sphere is principal curvature is 1 over r. So the mean curvature is defined usually with 1 over 2, with half of a sum of principal curvatures, and the Gauss is the product. And so they studied this for membranes, and it is, for example, this is also the picture for minimal surfaces, which are well known. So this is a helicoid, and this is the catenoid. Which is interesting is these two are isometric, so there is a diffeomorphism that keeps the lengths of curves when you can find the mapping from helicoid to catenoid. But also there are other minimal surfaces which are used now in these applications in physics and biology. This is well-known Schwarz, and remember me on Schurk, so this Schwarz minimal surface periodic, and then you can find these applications in biology. So as I said, Gauss curvature, Gaussian is defined as the product of principal curvatures, mean is average of principal curvatures, and by simple arithmetic calculations you obtain this inequality. So what you can deduce is that this is the inequality. This is extrinsic invariant, and on the right hand side it is intrinsic Gaussian curvature. So this is one of the first inequalities that is well known, that it says information about extrinsic and intrinsic geometry. What I used also in my work for several times is in some invariants which are introduced by Chen in '93. This is a well-known delta 2 invariant, which has this is a scalar curvature, and this is the infimum of sectional curvatures. And this inequality is of this type. So this is his first inequality, and it somehow relates the mean curvature, which is the extrinsic invariant. This is also the constant sectional curvature of the ambient space, and the delta is intrinsic invariant. So this is intrinsic and extrinsic. So this is what we study recently also. So later in his book he introduced many other invariants, and also he has a part in his book about pseudo-Riemannian geometry, and he was trying to relate these extrinsic, intrinsic to obtain another conditions on immersion in a real space form mainly. For example, one of the theorems, because I think I will not have time to speak about it, is like this. So we studied this submanifold of S7, and we obtained under some conditions, which I will show, we obtained the immersion. But this immersion was, as I said, you pose a condition, you do blah 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 some computations, and you obtain the immersion, and you do not understand anything with this immersion. It is some mapping, and you don't feel it. And then in another paper, we were able to conclude that this immersion is exactly the immersion of a product of two spheres. So we studied 5-dimensional submanifolds, and we obtained some immersion. But this was really the warped product of two spheres S3 and S5, and we proved that it satisfies some conditions. It is minimal, which I just mentioned, and it satisfies some Chen-type inequality. So I will not I will not explain now what is what, but this is a relation of extrinsic and intrinsic invariants. This is more simple, but the point is that you try to study this. The one I mentioned, this inequality, is the first one from '93, is that this product of spheres is a delta 2 ideal. What means ideal? It means that here it is equality. So Chen especially studied these manifolds where it is equality sign, and he called them ideal, which means that from the physical point it is ideal. And he also, in his talks, he likes to talk about these invariants. He likes to say that it is the best way to live in the space, and then he knows how to connect it with the everyday life and so on. So now turn to more formula. So what we will study today is we have a Riemannian manifold, although I said there is a book from Sharma and Dugal about CR submanifolds of pseudo-Riemannian geometry. But I will work on Riemannian manifolds, and my metric on the submanifold will be, by immersion will be isometric. So the metric will be induced in an isometric way. And with the metric I have a tangent and a normal bundle, which will be very useful. And then I can write the connection. This is the connection in the ambient space as the tangent part and the normal part. And after some computations, it can be proved that this is also the Levi-Civita connection. I will not go into details for those who don't study it, but it is a metric connection without torsion. And it can be proved that this connection is also without torsion and metric. And this is what we call second fundamental form, which is the normal part and which gives us very useful information about the embedding of the submanifold in the ambient space. This formula is called the Gauss formula, and if we try to find how the normal vector field behaves with respect to the connection of the ambient space, we also decompose it into tangent and the normal part, and it can be proved that this A, usually it's denoted by A, is the shape operator with respect to the normal psi, and this is also the linear connection in the normal space. There is also a very nice connection between the shape operator and the second fundamental form. This formula is in the theory of submanifolds called Weingarten formula, and these two formula give us interesting equations and relations for further study and for obtaining algebraic computations. A very important notion is a notion of totally geodesic submanifold, which says that asks that every geodesic on a submanifold is a geodesic on the manifold, and usually it's defined as a submanifold where the second fundamental form vanishes identically. For me, this should be proved, and we prove it in our book, because this is a more algebraic condition, but this is a very nice geometric condition. So if every geodesic on a submanifold is geodesic in the ambient manifold, we call it totally geodesic. And of course, it can be checked if the second fundamental form vanishes identically. Also, if the shape operator is special like this, so we know that this is for spheres. So this means that when you watch the behavior of the tangent of the normals, for example, in the three-dimensional space, this means that in any direction the normal changes in the equal manner. So, for example, on a sphere or on the rotational ellipsoid on these parts, in these surfaces are very useful in the study, and they are totally umbilical submanifolds. Submanifolds. So we are trying to classify submanifolds and to obtain under some conditions, for example, these two kinds. And for example, the old result is if the ambient space is Euclidean space, then it's totally geodesic is Euclidean space, which you can also just by definition think it's like that. So if you have some submanifold in the plane, and if you want that the geodesic is the same, somehow you think that it should be the plane. Or for example, if you want to find a totally umbilical space in the Euclidean space, if you want it to be complete, then it is n-dimensional sphere. If you don't say complete, then it is a part of a sphere, and so on. So what I said is that I want to study submanifolds when the ambient space has some special structure. So today I will try to say something when the ambient space has a complex structure or complex structure. So if, as Anna said, if you have the endomorphism, which is acting on the tangent bundle as similar as the complex unit in the C2, in C, sorry, then we call it a complex, almost complex structure. And if this almost complex structure acts as isometry, in other words, it satisfies this condition, then we say that it's a Hermitian metric. So we can skip this and save some time. So if this form is closed, then it is a Keller manifold. But what we use in differential geometry a lot is that this condition is equivalent that the structure is parallel, which means that it behaves the same in all tangent spaces. And this is a very nice geometric condition, and this also gives a connection with symplectic manifolds, and everybody likes, especially if you're on a conference with physicists, then it is very important to mention symplectic manifolds. What we also studied is when this is not parallel in all directions, so it is weaker conditions, and then some manifolds are called nearly Kähler manifolds. And what I did with my former PhD students, two of them, it's with the one I did a nearly Kähler 6-dimensional sphere, and with the younger one I did a nearly Kähler product of two 3-dimensional spheres, so S3 cross S3. It is, these are very recent results, so S6 has many results, but S3 cross S3 is very difficult to take the computations, and there are not many results. For example, we started for his PhD to find geodesics on S3 cross S3, and it was one paper, so it's a lot of work. Now they are studying CP3, which is one more, and there are 4 homogeneous nearly Kähler 6-dimensional submanifolds, and this 6th dimension is very important because all nearly Kähler manifolds can be decomposed as a product of 3 spaces, and one of them is exactly this 6th dimension, and that is why it is very popular to study them. Now we are doing some other things on it, but I will not talk about it today. So what we also mentioned today is, and what Livia mentioned is, what if we have a real hypersurface of this almost complex, or doesn't matter today, complex manifold, then if we decompose this, when we act with almost constant structure on a tangent space, we again have a tangent component and a normal. So it is a real hypersurface, which means we have only one normal, and the other condition is clear. So we have this distinguished tangent vector field U prime, and it was shown, I will show on the next slide, I think 60 something, 65, that this F is a skew-symmetric endomorphism, and that U prime is one form, S63. So this structure is the so-called almost contact, and under some conditions contact structure, which is also very well studied and important. So as I said in the introduction, this almost complex manifold is even dimensional, so this real hypersurface is odd dimensional, and nowadays, after so many years, that we say in our talks that it is a naturally induced almost contact structure, although at that time it was not so natural. So we also can obtain some features of this skew-symmetric endomorphism. So instead of almost complex structure, you don't have only this minus x prime, but you have also this additional term. So this is almost contact structure, as I said, naturally induced. So what we try is to generalize this case, so not to study only real hypersurfaces, but for example, this is the same, just to remind us about the notation. So we study the J invariant subspace of a tangent space of some manifold. So J invariant because this is the intersection of tangent and J acting on the tangent space. It is called holomorphic tangent space, and it is the maximal J invariant subspace of the tangent space. The dimension of this space can vary from point to point. So we have examples, very simple, that in one point it is one dimension, but what we prove is that this dimension can be the dimension of submanifold or n minus codimension, and it is always between these two dimensions. If this dimension is constant, then we call it Cauchy-Riemann submanifold. I use this Cauchy-Riemann, although it is not clear if it was Cauchy-Riemann. There are many stories about this. Some people say that it is because of complex real, because it is also in some intersection of complex and real submanifolds. This definition is from 65, but there is also another definition which many people working in differential geometry, so this definition is used more in complex geometry and in global complex geometry. This one is used more in the family of people working in some manifold theory. So two important situations occur. This means that distinguished situations. This means that the whole tangent space is J invariant, and then we call it complex submanifold. So that is why I wrote real hypersurface and real submanifold. This complex means that this is J invariant or holomorphic. And the other case is when this J maps the whole tangent space to the normal space of the ambient. And in that case we call it totally real. And what Bejancu did in 78 and later in 79, he somehow generalized this definition, and he called this, there are rumors that he called it first complex real submanifold, but since he died, we tell that only as a story, that this distribution is such that this part, this D, is J invariant, so holomorphic, and its orthogonal complement is anti-invariant. So the special cases are the case when it is holomorphic or complex, which means that this D is the whole space. And the other case is when this is 0, so when all tangent space is mapped to the normal. So these are the distinguished cases studied in the 70s, and this is 1970 something finished. And this, as I said, this is J invariant, so when this, also this is from the other definition. And real hypersurface is case when having in mind the Bejancu definition is where this D is n-1 dimension, and D perp is only one vector field, and it will be, you will see this U vector field. Totally real, as I said, is when all tangent space is mapped to the normal space. What we studied is CR submanifold of maximal CR dimension. I missed somewhere that this... sorry, I did not mention this, what I wanted. So if it is important, if M is CR submanifold in the sense of Bejancu, it is a CR submanifold in this definition of complex analysis people. Sorry, these are examples. And if this dimension of holomorphic space is n-1, so it is the next, because if it is n, then it is invariant. It is already studied. Many results are obtained, and there is, I don't know if there is anything that can be proved. So the next dimension is one lower, it is n-1. As I said, we tried with n-2, but even with examples we had many problems. So we left it to young people. In that case, there is a distinguished vector field Xi, so that J acting on the tangent space can be represented with the tangent part and the normal part, which resembles us of a real hypersurface case. But what we are interested now is, do we have other examples? Because if we have only real hypersurface case, then we did not do anything. We go back to real hypersurface case, which is already studied and finished. What is important to say is, if it is a CR submanifold maximal CR dimension, then these definitions coincide and we don't have to worry about it. So we have examples. As I said, real hypersurface is the first example, and it can be easily proved, but the next one is not so clear. So I already have these definitions, so we know what is complex submanifold, and we have many complex submanifolds, so the codimension is very big. So we can have, for example, 4-dimensional submanifold in 8-dimensional. So any complex submanifold, and then take its real hypersurface. And we can prove that it is CR. The proof is not so obvious, and it is given as example 15.2. And also this is more difficult to prove. So as I said, we can study real hypersurfaces of almost Hermitian manifolds. We already mentioned it, and they showed that there is f prime structure. This is this almost contact structure. And then we study F prime invariant submanifolds of it. So here it's somehow opposite with the previous example, which means we have a hypersurface and then F prime invariant of any dimension for the beginning, but then we proved in one paper that it cannot be even dimensional. There is a proof, blah blah blah, that it has to be odd dimensional. So in these two big class of examples, we have showed that that there are many examples even of CR submanifolds of maximal CR dimension, not only the real hypersurfaces. I mentioned here example 15 something. Sorry, this is a maybe I don't have time for this, but what we are trying now is to prove that this, if you decompose it into these two tangent and normal components, we show that this F is also almost contact structure, which is good. And we showed it. So these examples are from our book about CR submanifolds, especially of complex projective space, although we studied also of Euclidean and hyperbolic spaces, but not we did not prove all theorems for all three spaces. We left it for, because after some time you leave some things for later. So here in this book, in the first half, we gave the basic material about complex manifolds, and there are some manifolds. So a small part is about submanifolds themselves, and then submanifolds of Euclidean spaces, of spheres, then of complex manifolds, where we proved all these things about almost contact structure, which is induced by J. And in the second part, we gave some of our results, not all, because the idea was to make just a small book. For example, we gave all our results like this. So it is very important to study eigenvalues of shape operator of every submanifold. For example, in the case of hypersurfaces, the first papers were like if the shape operator has a constant principle of curvature, then we have this classification. So it is very important to study eigenvalues, and when they are constant, we are very happy because we obtain very nice results. Also, as I mentioned, this is a second fundamental form, and this is a structure which is naturally induced from the ambient space. So we study this in almost Hermitian, then especially in Kähler manifolds, although there are some papers by my students, for example, CR submanifolds of S6 I did, but of S3 across S3. Some young people are doing this. So it is very nice to have this structure and to combine, as I said at the beginning, the interplay between structure, which is extrinsic, second fundamental form, which is extrinsic invariant, and structure, which is intrinsic. It is only submanifold. It is induced by J, but it is inside. So this condition is equivalent to the condition in real hypersurface case, where this almost contact structure, which I mentioned, and shape operator commute. So these are famous results: A phi equal to phi A. So classify real submanifolds such that almost contact structure and shape operator commute. This was done in 1970 something. So we studied these conditions, and I chose only one result. It is this which I mentioned, and we obtained, for example, the theorem for all three ambient spaces. So especially we studied for some papers, we studied when the ambient space is especially complex space forms, which means that the holomorphic sectional curvature is constant, and then we know that they are of three types. This constant sectional curvature is 0, this is the first case, positive or negative. And we obtained for a complex Euclidean space, you can say this is Euclidean space, a sphere, which is something to expect because we have the second fundamental form, product of spheres, okay, but what is this? Or is this in complex hyperbolic space? we don't talk about this today, but these are the model spaces, because in a complex projective space, which is the first, how to say, after the complex Euclidean, from its complexity, but also from the number of papers where people study, there is a lack of totally geodesic and totally umbilic, so that you don't have hypersurfaces like this. So this is some published somewhere. So when you study complex projective space, you always have in mind the Hopf vibration from the odd dimensional sphere, and then you have the submanifold, which is a product of two odd dimensional spheres, and the Hopf vibration of it is this model space of complex projective space, and it is very well to obtain its characterizations, and one of these is one I showed. So now I will switch a little bit to CR submanifolds of odd dimensional spaces. We already introduced what does it mean contact structure. Here by purpose I changed F to phi, just not to mix with the previous slides. So here phi is this skew symmetric endomorphism. Our manifold is now odd dimensional. And what we want is somehow to study similar submanifolds to CR submanifolds. And that is exactly what this is a Sakian. It is a manifold which is somehow odd dimensional equivalent for Keller manifold. And Bejancu studied in 81, and here he called first semi-invariant and later CR. Because of some pressure, yes. So how he defined it? If there exist two distributions such that exist distributions such that one part is phi invariant and the other part is anti-invariant, then we call it contact CR submanifold. It is somehow natural to study this because in the, if you remember, in the complex case, instead of phi we had J. Here it is a problem of this Rib vector field, I did not call it Rib, but this is this psi, where to put it in D or D perp, but results are the same, doesn't matter where you include this. It is well known that there is a Sasakian structure on odd dimensional sphere. The Sasakian structure, as I said, is something which is odd dimensional variant of a Keller manifold, and it is defined in a very natural way because a complex structure is defined in a natural way in the space R2m plus 2 dimensions, and this sphere is then its real hypersurface, and then we define psi as Jp. So P is the position vector on the sphere, and Jp is then a tangent vector, which will be a characteristic or Rib vector field for the contact manifold. And then we can prove that this phi, which is then a tangent part, is almost contact structure on the sphere. And we can study the case when psi is normal. It is already studied in this book of Jano and Kohn. It is phi anti-invariant, which is already studied. When psi is in some strange position, it is very, very difficult to compute. So nobody is doing this. So what people are doing is when psi is tangent to m. But unfortunately, in papers you don't see this because there are now many, many papers from some countries on this topic. They write, let psi to be tangent, but why to be tangent? Why don't you study other cases? But you don't study other because this is already studied and this is impossible to study. Nobody wants to do this. But if psi is tangent, then you have this decomposition of the tangent space, and we denote this as a phi invariant and E as an anti-invariant. Then if we study especially 7-dimensional sphere, then we know what can appear from dimensions. So this is invariant, so it has to be even dimensional, and these dimensions, they go out from these decompositions. So we have these three possibilities. So we can study 4, 5, and 7 in 6-dimensional case. What we did is we finished 4 and 5, and then COVID started. And then we I don't know what we did. We are lost in space and time. So for these cases, it is very easily showed that any contact submanifold in any Sasakian manifold can never be totally geodesic. But we are interested in studying totally geodesic submanifolds. So what we can do, we can study something similar to them. So we know now, we mentioned recently what is totally geodesic. And just to remind yourself, it is a totally geodesic if and only if H vanishes identically. So we know that in a Sasakian case, H, the second fundamental form, cannot vanish. But maybe people studied mixed totally geodesic, or we studied nearly totally geodesic. What does it mean? It is zero on this phi invariant space, and it is zero on this phi anti-invariant space, but not when you mix one from here, one from here. When you study this mixture, so when one vector is from H, another from E, then it is called mixed totally geodesic. Some other people study this. And with this, after some time, we want to find proper, this means not phi invariant or the other, to study all these nearly totally geodesic contacts. And we obtained some results before COVID. So as I told you, we obtained some immersions. So from this point of view, you don't see much because these are some mappings. And this is a 5-dimensional case, it is even worse. So what we do is choose appropriate base, some functions, then express shape operators, then compute Kodazzi-Ricci, and just to have impression, these are terrible, terrible computations. You obtain PDEs like this, then you compute some more formula, and these are these PDEs where you want to find some conditions, and from these PDEs you compute after several years this F, this immersion. And you obtain the formula, and you don't know what to do with this formula, because it is only you say this is some manifold given by this formula, but you don't see what is it, you don't see its geometry. And then after some time we proved that in the first case it is congruent to this product of spheres, but it is not the ordinary product, it is the warp product. But it was not clear at the beginning when we published this paper, and it happened a lot of time later, that we also found the warping function. And moreover, we found many interesting features of this, and this is published in another paper. This is something about warp product. And you know that warp product is something like this, has a lot of applications. What I want to show you is just one more slide for this. What we obtained for this special mapping, it is that, of course, it is nearly totally geodesic. We expected this, but now we computed it from another point of view. It is good that we obtained this because we obtained this from another way, imposing conditions. But what we did not know is that it is minimal, and we did not know that it satisfies this equality of Chen-type equality. So it has some equality. This means it is ideal in this sense, but it is not this basic chance inequality, but it relates also second fundamental form, which is extrinsic, and some intrinsic invariance. So we obtained this special, nearly totally geodesic submanifold has also some nice features, and we obtained, sorry, this is, I cannot find, it is also delta 2 invariant after some computations. But as far as I see, this is the computer. I think that my time is over 2 minutes ago, so I thank you for your patience. I was talking several minutes more. Sorry.
You.
Any questions? Max?
I have no question, but I have a remark. Quaternionic geometry is very well represented. which is parallel with Keller geometry. Corresponding to Keller geometry, you have four-task geometry, which in parallel you have three structures. Bejan and Papaduc defined semi-Riemannian submanifolds in the sense of CR. But then all theory stopped, probably because both died, Papaduc and Bejan. But I thought, since you have this huge experience with such CR submanifolds, maybe it's interesting to see what happens in quaternionic case.
Thank you for this remark. I tried with Professor Matija Fava, because he did a lot of things. Yes, because he visited Belgrade and I went to Rome, and then we tried, and we were not able. Then I tried with Max Pontecorvo, and nothing. So I don't know. You're right. I gave up at some point, but it is a very good remark. Maybe I have now more experience because this I tried I think 10 years ago. You're right. It should be continued.
There are a lot of directions of studying, in the sense of analysis, in the sense of topology, some invariants, in the sense of harmonicity of some structures. So there are a lot of directions to follow. It's impossible, at least one, not to go to somewhere.
Yes, thank you. This is a very good remark. Also, there is a story of CR manifolds and CR submanifolds, but to compare this. But this with quaternionic we really tried, because then we had this cooperation with the Rome University, but somehow we could not move.
Because of huge calculation, or what was the reason?
Because we did not have any examples that could justify why somebody would study this. It was more technical. So you can take a structure and then compute, but we did not have any. So that is why I spent some time to show that really these things exist in the nature.
So I understand once an example, an interesting example is constructed, then what theory can work.
Or you, I don't know if it's can work. No, it can work. Theory can work itself, but somehow there must be motivation why to do this, because there are you know that there are some people that are studying like quasi trans, also they are studying CR. I obtained many papers like this. Then what we studied is some manifolds of complex space forms, but they study CR of trans quasi with all these adjectives from. So, but why to study this? And then you tell them, okay, the paper can be accepted with you if you write the example, and then they write some not nice example.
Oh, I
only a low dimension with the, how to say, with the artificial metric or something very artificial. So in that sense, I thought example.
thank you.
Can I ask you about indicator, just a curiosity, which type of submanifold you get, for instance, for S3 cross S3?
For S3 cross S3, it is a good question, because for now we obtain only the immersion, and it doesn't look nice.
Okay.
Doesn't look nice.
Yeah. Okay.
That is why I mentioned this, because this really we were very happy, because we found even the working function. So we found everything. But for C3 cross C3 it is very difficult to find. For S6 it is okay, because if you pose enough conditions, and then you obtain a circle, you obtain an intersection of a sphere with some Euclidean space of lower dimension, but it is some kind of also of sphere. And for S6 it is easy, and there we have nice results. We studied with Luc Franken. We studied this submanifolds. C are submanifolds which satisfy various kinds of channels equality, and you obtain nice results. But for C3, it is not so.
Okay, thank you very much.
Other questions or remarks? If not, let's thank the speaker again for being nice. Lunchtime we're starting a slow coffee.
I would like to invite all the participants before going to lunch to go outside in front of the institute and take a joint photo.
Моят телефон нещо е проблема, не е по принцип със сайта.
The first talk is by Raul Tănase from Institute of Mathematics of the Romanian Academy of Sciences, and it is about the critical locus of a dynamical system. Please.
Thank you very much for the introduction and for the opportunity to give a talk at this nice conference. I will speak about holomorphic dynamical systems, focusing on the role of critical points in one complex variables and the dual role of critical varieties or critical loci in dynamics in several complex variables. Whenever we talk about dynamical systems, we usually start with a function which models the evolution of a system over time. For the purpose of today's talk, I will have a polynomial function, at least when we talk about dynamics in non-complex variables. So it will be such a function, a polynomial of degree d, going from the complex plane to the complex plane, where the degree of the polynomial is greater than or equal to 2. And in dynamical system, we wonder what the behavior of points is under successive iterations of this function. We take a point z in the complex plane, we apply the function f to it, we get f of z, then we get f of z, f iterated n times of z, and we wonder what happens to this point as n goes to infinity. And of course, it may be a very difficult question to say exactly what happens to each and every point. So we wonder about the qualitative behavior of points. For instance, do they have sensitive dependence on initial conditions? If we pick a point and we look at the points in a small neighborhood around it, do they do the same thing or do they behave in very different ways? Some converging, some diverging, or accumulating on various pathological objects. And it makes sense from the dynamical point of view to first do a division of the complex space into these sets. So first we talk about the set K of points which remain bounded under Floyd iterations. They do not diverge to infinity. The complement is called the escaping set. These are points which are eventually attracted by infinity. And sitting as their topological boundaries is this Julia set, which we denote by J. Now, even before other definitions, one can see that points in J do not have stability because they do not behave in the same way in a small neighborhood, because if you take a point in this boundary and you take a small neighborhood around it, it will contain both points with bounded orbits and points which converge to infinity under Floyd iterations. So this Julia set J is a set on which we have instability, and this is usually a fractal set in C, whose topology is something that dynamical systems hope to understand. Now, it's more or less folklore that when we talk about polynomial dynamics in one variables, the important role in the topology of the Julia set, as well as in the dynamics of the Julia set, is played by the critical points. Critical points, they have the same definition as for regular analysis. You just take a function, you differentiate it, you set the derivative to be equal to 0, and you discover, in our case, because we work with a polynomial of degree d, that we have d minus 1 critical points counted with multiplicities. And it's a folklore statement almost, due to many authors, that critical points, they determine the geometry and topology of the Julia set. A first theorem to this effect is the fact that we can decide the connectivity of the Julia set based only on the behavior of the critical points. Namely, the Julia set is connected if and only if all critical points of F belong to K, so they don't escape to infinity under Floyd iterations. This gives us a very simple criterion for deciding the connectivity of the Julia set J, which is a fractal object, it has many points, But all we need to do is to track down d-1 critical points and to see what their behavior is. And the fundamental question, of course, is if there is a proper analog in 2 dimensions where same things you will see turn out to be a little more complicated. Another theorem over here which helps us visualize the importance of critical points in one-dimensional dynamics is provided by the Sullivan's no-wandering domain theorem. This is also a famous theorem in complex variables. And just to say roughly what it says, let me point out that a periodic point of period n for a function is just a point which is fixed by the nth root of the function. So we'll refer to it as a fixed point, for example, if f of z is equal to 0. And then the multiplier over here is simply the derivative of the nth root of the point. And as it turns out, if the derivative over here is less than 1, the point is going to be attracting. So nearby points are going to converge to it under 4 situations. If the derivative over here is greater than 1 in absolute value, the point is going to be repelling, so it's going to repel everything in a small neighborhood. And if it has absolute value equal to 1, well, the situation is a little bit more complicated because it depends on the arithmetical properties of the eigenvalue. Sullivan's no-wandering domain theorem over here tells us that basically any component of the interior of the set of points which do not escape to infinity under Fourier iterations is eventually periodic. So eventually periodic means that under a finite number of iterates is going to become periodic. Let's just assume that it's fixed. Let's just assume we have a fixed component. Any such fixed component is going to be classified as the basin of attraction of an attracting fixed point, which means that all the points in the interior of this component are going to converge under 4 iterations to this fixed point, and this fixed point is going to be an interior point of the component. In the second scenario, all the points in the component are going to converge, but not to an interior point of the component, rather to a point in the boundary of the component. This is what the parabolic point represents. And in the third scenario, we're going to have a so-called Ziegel disk. So the fixed point is going to be in the center of a component, and all nearby orbits are going to rotate, are going to basically move around circles around this fixed point. Now, the importance, this theorem is of course a deep theorem, but what I would like to emphasize on is the role of the critical points here, because there is a theorem of Fatu and Shishikura saying that we can have as much of these components as the number of the critical points of the polynomial. So in one dimension, or at least for polynomial dynamics, there is a bound on how many different scenarios one can have in the interior of the points of the set of points which do not escape to infinity under 4 iterations. Now, let me illustrate what I just said with a couple of pictures. The advantage of working in dynamical systems is that one is always able to produce some sort of pictures to illustrate the phenomena over here. These are some polynomial Julia sets, and what you see over here in black is the set of points which do not escape to infinity under 4 iterations. What you see over here in different shades of red and yellow is the set of points which escapes to infinity. And at the boundary, you see the Julia set. The Julia set is the fractal object over here representing the boundary between the black and the colored region. Now, as one may see over here, there are many components of the interior of the black. Basically, everything like this, and you can see the self-similar pattern repeating everywhere in the Julia set. You can see many components over here, but what Sullivan's theorem says is that there aren't so many actually, because most of them they're pre-periodic. And it means that if I take a point over here, it's gonna iterate under a couple of iterates to one of these three components which form a cycle. So there is a periodic orbit of period 3 over here, which is attracting. It has multiplier less than 1. And if we take any other point in the black under forward iterations, it's going to converge to this 3 periodic cycle. And the same thing happens wherever we place ourselves in these other components of the interior of the black region. This is not to say that points in the boundary behave in the same way. We are just talking about the interior of the black region. Over here, to the right, we have a Ziegler scenario, which means that we have a fixed point over here with multiplier of the form e to the 2 pi theta, where theta is irrational. And if we pick a point somewhere in here, what it's going to do is it's going to describe a circular orbit around the critical point. Such an orbit is depicted over here. It's like a circle, real analytic circle. And on the boundary of this component, we also have a circle, which is just a topological one. Again, all the other components of the interior of the black are eventually iterated. Let's say this one will be iterated maybe under 2 iterates onto this component, and then the circular motion is going to happen over here. In the last scenario, we have a parabolic fixed point, which is just here. And the parabolic fixed point is now in the boundary of these components. And everything in the interior of the black region is going to get attracted to this boundary fixed point under forward iterations. What you see over here, the flowery-like shape, is because we take a point in the black and it jumps from this component to this component to this component. But if you just take the second iterate, this is what it will do. It will converge over here. Repel at first and then attract. Okay, so these are some types of dynamics that one visualizes quite nicely in 1 dimensions. And let's just focus on quadratic polynomials for the time being, so I can illustrate more the importance of the critical points. For a quadratic polynomial, it's really easy to compute the critical point because we only have one. We take this family, z squared plus c, where c is a complex parameter. This is actually quite a famous family because it's the one which produces the Mandelbrot set, which maybe you've seen if not studied. We have only one critical point, z equals 0, which you see at the center of these pictures. And as the theorem, the first theorem says, we can decide the connectivity of the Julia set just based on what the critical point 0 does. For example, over here, the critical point itself is periodic with period 5, which means that it does not escape to infinity, hence the Julia set is connected. We only have one critical point. It's easy to test the connectivity in this set. What happens though with the other fixed points? Because over here, the critical point itself is also a fixed point of period 5. The multiplier is equal to 0, because this is also a critical point. Everything else in the black gets attracted to this cycle. Okay, we've established that. But where are the other fixed points of the polynomial? Because we are in the complex setting, and so this one has 2 fixed points, but it has 2 to the n points of any given period n. So all the other points over here, they are going to be in the boundary of the black. They are going to be over here in the fractal Julia set, and moreover, they're going to be dense in this fractal Julia set. Okay, now let me go over to another picture, and then I'll take a small break from pictures. this is showing a disconnected Julia set for a quadratic polynomial. What we see over here is that there is really no black, but I mean there is no black in the sense that you don't see an interior to the Julia set. However, we know that there are many points in the Julia set because we've just established that all the periodic points, they cannot possibly escape to infinity under 4 iterations. Moreover, they're dense in the Julia set. So at least their closure, but actually that's a theorem that the closure of the rebellion periodic points is the entire Julia set. We see that everything over here is just the Julia set itself. There is no interior. Okay? But because we work in the quadratic setup, more can be said. This is the point 0. Our test for connectivity is easy. You see the orbit of the critical point 0 escaping to infinity. The Julia set is disconnected. And because we work in the quadratic setup, we know that the Julia set is actually going to be totally disconnected. It's going to be a Cantor set. And there is a nice combinatorics which associates to each point in the Julia set a one-sided sequence of zeros and ones. The polynomial acting on the Julia set, because the Julia set is an invariant set, so we can restrict the polynomial to the Julia set, is actually topologically conjugate to the so-called shift map on this space of one-sided sequences. And the shift map just forgets the first position and it moves all the other points to the left. Okay, so these are the Cantor sets that correspond to, based on the dynamics of the critical point, we are able to say not just that the Julia set is disconnected, but we are actually able to describe a topological model for the Julia set. Okay, and now a concept which pertains to one complex dimensions, but also can be generalized to higher dimensions, is the concept of hyperbolicity. In one dimension, we say that the map is hyperbolic on its Julia set if there is a metric on the neighborhood of the Julia set, such that the derivative of the polynomial function is expanding with respect to this metric. And it's more or less obvious that a function is hyperbolic on its Julia set if and only if the closure of the orbit of the critical point is disjoint from the Julia set. There isn't much we can adjust in a metric to make a critical point where the derivative is equal to 0 expanded. So you can feel the flavor of this theorem and the need for the orbit of the critical point to be disjoint from the Julia set. But why we like hyperbolicity is that it gives some structural stability. And what do we mean by structural stability? A map, if we just fix a parameter c over here, and we consider the polynomial f index c, which is z squared plus c, on its Julia set jc, it has no structural stability, as we saw. Some points in the Julia set, they stay bounded, but in a neighborhood, some other points go to infinity. So on a particular Julia set, we do not have structural stability of the map. But there is a notion of structural stability as a function of parameters. So if we take f of c, a polynomial which is hyperbolic on its Julia set jc, and if we perturb this parameter c, then we create another map, f index c prime, which is z squared plus c prime. And the theorem over here says that the new map is also going to be hyperbolic on its Julia set. And moreover, there is a homeomorphism going from one Julia set to the next Julia set, which conjugates the map, the initial polynomial, with the second polynomial. And you can see that such a relation over here is composes nicely under iterates. It means that the two polynomials, they're going to have the same dynamics. They're going to have the same dynamical properties. They're going to have conjugated Julia set, but also conjugated dynamics. Okay, so sometimes this is philosophically called as making order out of chaos. There is chaos in in every one of these polynomials, but it's a chaos that looks like the chaos of a neighbor. Okay. And this is a picture of the Mandelbrot set, which you may have seen. So what it stands for is the set of parameters C for which the Julia set JC of the polynomial f index C is connected. This is a parameter picture. It's not a dynamical picture, but it also looks like a fractal. And it's easy to draw it, unlike other parameter pictures for, let's say, higher order dynamical systems, but even for lower order dynamical systems, precisely because of the critical points. We have a very clean test for the connectivity of a Julia set of a quadratic polynomial. So all we need over here in order to produce this kind of picture is to take a parameter C, look at the polynomial z squared plus c, look at the orbit of the critical point 0. If it escapes to infinity, then we color it in red. If it does not escape to infinity, we color it in black. We call it a very nice picture. It's a clean and clear algorithm. There aren't many such families in higher order dynamical systems, as you will soon see. Now, going back to the picture of the Mandelbrot set, it's not as easy to visualize the Mandelbrot set as it may seem from this picture, because there are many self-similar copies of the Mandelbrot sets, there are many filaments over here and other self-similar copies of the Mandelbrot set, so it's a complicated fractal set in its own right. It's a theorem of Douady and Haber that the Mandelbrot set as a set is connected, and it was a question of whether this is also locally connected. Now, what may have seen as a basic question about the topology of a set turned out to be a very important property, because it implies the local connectivity of the Mandelbrot set, which is still not proved. It implies a lot of other theorems which are very important from the dynamical perspective. For instance, this is the Fatou conjecture of the density of hyperbolicity conjecture, which says that the set of parameters C, for which the polynomial of C is hyperbolic on its Julia set, is actually dense in the complex plane. So basically, any kind of polynomial can be approximated by hyperbolic polynomials. Now, this theorem over here would be most relevant for the polynomial in the boundary of the Mandelbrot set, because if we take a point in the boundary of the Mandelbrot set, these are not going to be polynomials which are hyperbolic on their Julia set. If they were hyperbolic, then they would be structurally stable. It means that any nearby polynomial will do exactly the same thing, either in the black or in the red. This is not what happens on the boundary. So on the boundary of the Mandelbrot set, we do not have hyperbolic polynomials, but the theorem over there says that it's not a theorem, it's a conjecture, says that they are approximated by hyperbolic polynomials. And the MSC conjecture, which is that the Mandelbrot set is locally connected, it is proven to imply the Fatou conjecture, which is the density of hyperbolicity conjecture. Now, this has been solved for many parameters on the boundary, but it's still an open problem. And it's quoted as one of the problems that would get the solver a Fields medal. So it's, regardless of its quite, let's say, tame aspect, it is one of the deep problems in one complex variables. Okay, so we've emphasized a little bit about critical points in one-dimensional dynamics. Now let's change a little bit the setup. We are still in the polynomial context, but now we move over to two variables. And we would like to study polynomial functions in two variables. Now, in one variable, the easiest functions with non-trivial dynamics were just the polynomials of degree d greater than or equal to 2. In one dimension, we don't really discuss about polynomial automorphisms of the complex plane because these are just linear maps. They're maps of the form alpha z plus beta, but these have rather simple dynamics. They're not of interest to us. However, in several variables, there are many polynomial automorphisms of C2 which have very interesting and non-trivial dynamics. There is a theorem of Friedland and Miller from 1989 telling us what kind of families of polynomial automorphisms one could get up to dynamical conjugacy by another polynomial automorphism. And it says that every polynomial automorphism is conjugate to one of the following maps. The first class is affine maps, a matrix times xy plus a translation factor. It's basically the analog of alpha z plus beta, the one that I've told you from one-dimensional dynamics. The matrices here is assumed invertible, but that doesn't make the affine maps more complicated in terms of dynamical systems. So we view these ones as maps with simple dynamics and sort of not so interesting from the point of view of dynamical systems. Then there are the elementary maps in which one coordinate evolves independently of the other. There are called functions with decoupled dynamics. So y goes to by plus c is just a function of y. And then the first coordinate is a function of both x and y. These are not so easy as the first category, but they're sort of as complicated as one-dimensional dynamics is. And then there is the third category, which is compositions of Henon maps. And these are maps of the form xy goes to p of x minus ay and x on the second coordinate. A over here is actually the Jacobian of the map. These maps, they have constant Jacobian, which is equal to a. When a is different from 0, we've got a polynomial automorphism of C2. When a is exactly equal to 0, this map is no longer invertible, but it sort of reduces to the dynamical of the polynomial b. And sometimes this gives us an insight into several dimensions, starting from the dynamics of the polynomial b. There are actually many other theoretical motivations for studying Henon maps. They weren't quite introduced the way I'm presenting them. They were introduced to model a physical phenomenon known as atmospheric convection. It's about the air which gets heated up by the Earth's surface. It raises until it cools off in the upper stratum of the atmosphere. Then it goes down again, and it describes some sort of motion, up and down motion, which is hard to understand. And to introduce a simplification of this model, the Henon, Michel Henon proposed this Henon map. So it came as a simplification of a physical phenomenon, but people discovered that it had sufficient complexity that it produced chaotic dynamics and tons of other phenomena which are not seen in one-dimensional dynamics. So it became important in its own right. Now, from the point of view again of dynamical systems, since we have a map which is now invertible, unlike the polynomials in one dimensions which could only be iterated forward, now we have a dynamical system which can be tracked in both forward and backward time. So when we discuss the dynamics, it makes sense to do two kinds of definitions. K plus and K minus are going to be the points in C2 is bounded forward, respectively backward orbit. U plus and U minus, the complements in C2 are the forward escaping set, respectively the backward escaping set. J plus and J minus, they're going to be the topological boundaries in C2. And J is the intersection of J plus and J minus. It's not obvious from the definitions, of course, but J plus and J minus, they're unbounded, connected sets in C2, they have a flavor of three-dimensional objects, and in some senses, in some cases, this is what they are. J over here is always bounded, and it may or may not be connected depending on the parameter C and A of the Henon map. All these sets, J plus, J minus, and J, they are fractal sets. The dynamics on them is chaotic. Okay, now there are many differences between one dimensions and two dimensions. Some differences, they come from the methods. Maybe some phenomena in several variables, they're in spirit the same as the phenomena from one-dimensional dynamics. But the methods, they are so different that it makes it harder to generalize the proofs from one-dimensional dynamics into several dimensions. And the differences, they arise basically from complex analysis, because complex analysis in one variables and complex analysis in several variables is very different. Tools like the uniformization theorem, the Riemann mapping theorem, they do not have proper extensions in several variables. And then there are the different phenomena over here. For example, for Henon maps, which are polynomial maps in C2, the number of attracting periodic points is not bounded by the degree of the map. Even if we start with, let's say, a quadratic Henon map, there is no reason to expect any kind of bound on the types of dynamics that the map can have. There is this Newhouse phenomenon that one quotes usually when sustaining such a hypothesis, that there are indeed Henon maps with infinitely many attracting orbits, and between 1 and infinity there are many coexisting phenomenons that one simply does not see in one-dimensional dynamics. The other thing is, in one dimensions, critical points, they play a fundamental role in the dynamics, as we've seen. In two dimensions, for instance, the Henon map is a biolomorphism of C2, so it does not have any critical points in the usual sense. There is no point for which the Jacobian matrix is singular. But as we will see, on the other hand, the Henon map has lots of analogs of critical points which are useful in deciding the dynamics and the topology of the Julia sets. So I'm about to discuss such a notion of critical points, and before I tell you what this is, let me just give you a brief description of the dynamics of a polynomial automorphism. It's a very raw description. One divides the parameter space, the dynamical space, into three regions: V, V plus, V minus. And points in V minus, under four iterations, they can go to V plus or they can go to V. But if they end up in V plus, they're going to converge to infinity under four iterations. Under backward iterations is the reverse picture. Points in V plus, they can go to V minus or to V. But if they ever end up in V minus, they're going to converge to infinity under backward iterations. Which means that these escaping sets, U plus and U minus, they can be described as the set of points which eventually get to V plus. The same for U minus. It's the set of points which eventually, under backward iterations, get to V minus. And these are complex manifolds, U plus and U minus. And moreover, they have natural foliations associated to them, corresponding to the rate at which points escape to infinity. Some points they escape faster to infinity, some points they escape slower to infinity, and it defines a certain foliation of U plus by copies of the complex plane, which are immersed in complicated ways in C2, but they're still individually copies of the complex plane. They can be formally defined over here in V plus, because in V plus, the Henon map, I'm focusing on quadratic Henon maps here. If we have a polynomial of degree 2 and we are in V plus, then the polynomial is going to behave in some sense as x goes to x squared. This is what the conjugacy over here says. It says that if we are, let's say, close to infinity in V plus, then the Henon map behaves like x goes to x squared. And this function V plus, it takes values from V plus into the exterior of the unit disk. It's a holomorphic function, and its level sets define a holomorphic foliation of the set V plus. This holomorphic foliation, it can be propagated to the entire set U plus by means of dynamics, and it's the same thing over here. So we can understand these foliations as just foliations with copies of C created by the rate at which points escape to infinity under forward iterations, respectively under backward iterations. Now, these foliations are not everywhere transverse to each other. They may develop these kind of tangencies, and it's these tangencies that will play the role of critical points from one-dimensional dynamics. The picture over here sort of illustrates this phenomenon in a very schematic way. What we have on top, it could be a fiber of the foliation of U plus. It's a representation of a complex plane over here, which is bent and twisted in C2. And the other one, the one which looks more straight, could also be part of the same fiber of the foliation of U minus. And these over here, they could be tangencies between just two leaves of the foliations. Okay, so now let's look at all the tangencies between the foliation of the escaping set U plus and the foliation of the escaping set U minus. This is what we will call the critical locus C. It's a theorem of Bedford and Smiley, but it follows from general foliation theory that the set C is a non-empty, closed, analytic subvariety of the intersection of U plus and U minus, and it is invariant under the Henon map under both forward and backward iterations. Okay. In this talk, I would like to focus on the critical locus and show you some analogies that it may have with the critical points from one-dimensional complex dynamics. This is what a critical point may look like as observed from within a leaf of the foliation of U minus. Such a leaf is a complex plane. It's gonna intersect the Julia sets J plus and the U plus and K plus in such a way. So over here in black, it would be the set of points which don't escape to infinity under forward iterations. In green, it would be the set of points which escape to infinity under forward iterations. And over here, it would be such a critical point that this leaf, when immersed in C2, creates with the other foliation. So this would be the analog as regarded within this. Okay. Now, one can also introduce other type of critical loci over here, which makes sense for certain types of Henon maps. For instance, instead of looking at the tangencies between the foliation of U plus and U minus, one could look at the tangencies between the foliation of U plus and the lamination of the Julia set J minus. J minus is also, in some senses, in some cases, laminar, so it's laminated by the unstable manifolds of the points in the Julia set J. These are also copies of C, and they may create tangencies with the foliation of U plus. This is referred to as the unstable critical locus Cu, and the stable critical locus Cs, it's the set of tangencies between the foliation of the escaping set U minus and the lamination of J plus. What lamination of J plus? Again, when this set is laminar, it's laminated by stable manifolds of the points in J. Those are the points which eventually converge to points in J under forward iterations, and they form copies of C depending on the rates at which they converge at the Julia set. They contain points with the same kind of forward dynamics. It's not known in general what the relation between these critical loci is, between the set of tangencies between the foliation of U plus U minus, the foliation of U plus and the lamination of J minus, and the foliation of U minus and the lamination of J plus, but we know the answer in certain cases. So the general questions that one may ask over here is, what are the general properties of the critical locus C? Is it a set with singularities? Is it a smooth manifold? Can we produce some topological models? Can we connect the several notions of critical loci that one may formulate in several dynamics? And can we relate them to the dynamical properties of the map and to the topology of the fractal Julia sets? There are few cases in which a model of the critical locus is actually understood. One of them is due to Lubitsch-Robertson, which says that in a perturbative setting, the Jacobian of the map is assumed to be small. So the Henon map bears some similarity to the polynomial dynamics. More formally, if we consider a Henon map, which is a small perturbation of a hyperbolic quadratic polynomial with connected Julia set, you can visualize it as taking a polynomial from the interior of one of those components of the Mandelbrot set, and then forming out of it a Henon map with a small Jacobian. Then the critical locus is disconnected, and it consists of a primary component of the critical locus, which is asymptotic to the x-axis. It's not a random thing that it's asymptotic to the x-axis, because it's actually asymptotic to something which encodes the critical point of the polynomial. This primary component is biolomorphic to the outside of a unit disk. It's everywhere transverse to the foliations of U plus and U minus, and its boundary looks like the boundary which sits in the fractal set J plus, looks like the Julia set of the polynomial, so it's a fractal boundary over there. All the other components of the critical locus are just going to be iterates of this primary component under forward and respectively backward iterations. In this case, we have a connection. The Julia set is connected if and only if the critical locus is disconnected. We cannot exactly say if the critical point does not escape to infinity, but there is some sort of relation of this flavor. One object is connected if and only if the other object is disconnected. Now, I have used this kind of description for the critical locus to actually give a topological model for the Julia set J plus. J plus is a fractal object. It doesn't have a manifold structure, but in the cases where this description, Lubitsch-Robertson description of the critical locus holds true, so in the case of Henon maps that come as perturbations of a hyperbolic polynomial with connected Julia set, then we can describe the fractal Julia set J plus as a quotient of the unit circle cross the complex plane by a discrete group of automorphisms, which is isomorphic to z of 1/2 divided by z. The degree 2 over here, the number 2 over here, it comes from the fact that we work with quadratic polynomials, so it reflects the degree of the map. This group of automorphisms, it acts properly discontinuously and without fixed points on S1 cross C. So if we just factor S1 cross C by this group, we get a manifold. However, this cannot be exactly the model for J plus, because J plus in general is a fractal set, so it's not a manifold. So we need to quotient further by an equivalence relation, which is dictated by the polynomial. So it's quite an explicit polynomial relation. So there is a way to pass from the critical locus to models of the Julia set. Understanding one is important for the other as well. Okay, now in a different direction, but also with the aim of understanding the critical locus, we look now at Henon maps, which are going to be hyperbolic on the Julia set, but we look not for connected Julia sets, but rather for disconnected Julia sets. In several variables, it's not so easy to say the structure of a set which is disconnected. We cannot say that it's a totally disconnected set for any kind of Henon maps. But there are cases and classes of Henon maps for which this is exactly what happens. For instance, over here, it's a classical horseshoe pictures in dynamical systems, where the Julia set J plus is depicted in blue over here. It comes back and folds and comes back and folds, and it's sort of vertical like in spirit. The Julia set J minus is depicted in red, and it comes back and folds and comes back and folds and so on. And the Julia set J is at the intersection of these two objects. And it's a totally disconnected set. It's a Cantor set. The picture over here is only a real picture, but you can imagine these as being complex planes intersecting. And it's a Cantor set. If it's a Cantor set, then it has a binary encoding. All the points, they have binary encodings over here. The Henon map restricted to its Julia set is going to be conjugated now, not to the shift map on the space of one-sided sequences, because our Henon map now is invertible. So we need to conjugate it to an object which is also invertible. And so the conjugating space is the space of bi-infinite sequences on two symbols, zeros and ones, and the function which is conjugate to the Henon map is the shift map, the one that shifts elements by one position to the left. Okay, so we have this model for the critical locus in the case where we deal with such horseshoes. So we look at the Henon maps, H indexed by two parameters CNA, for which CNA obeys this kind of arithmetic inequality. The theorem over here says that there exists a region in parameter space, like this one, for which, for all parameters CNA, which belong to this region, which we call the H of V beta region, the critical locus of the Henon map is a smooth, irreducible complex analytic subvariety of U plus and U minus of pure dimension 1. It is connected. It is homeomorphic to a Riemann surface of infinite genus, which is a countable collection of truncated spheres with countably many handles between themselves, glued together by dynamics. It's a model that has been conjectured by John Hubbard, and it was previously proven only in perturbative setting. Now we prove it for a large class of Henon maps from the horseshoe region. I would like to stress first that in this case we have the backwards property. The Julia set in this case is disconnected, it's a Cantor set, but the critical locus itself is connected. So it raises the general question whether it may be a phenomenon for all Henon maps that would stand as a generalization of the role of critical points from one dimension. The Julia set is connected if and only if the critical point is the critical locus is disconnected. So let me explain a little bit about the model over here. Before we do that, there is also a relation between the three types of critical loci that I told you about. If we take this critical locus, which is this infinite genus surface, it has a big boundary. Actually, the boundary is the union of the two fractal Julia sets J plus and J minus, but the accessible boundary is in some case small, and it's exactly the union of the stable critical locus and the unstable critical locus, the one that we formatted. In conclusion, you understand not only the critical locus itself, but also its boundary in situ in this setup. Okay, so what is a truncated sphere for our critical locus model? It's formed by two hemispheres which are glued together along this boundary circle. And they resemble in some sense the polynomial dynamics. We take a Cantor-Julia set over here, the one that I've shown you in polynomial dynamics. This would be the critical point 0, which escapes under forward iterations, if we were to iterate it under the polynomial. Now, we don't go forward, we actually go backward. So the point 0 under a quadratic polynomial, it has two preimages, this and this. It has four preimages, this, and this. And we draw some disks over here around each of these preimages, and we remove these disks. Together with the removed disks, we also remove the Cantor set corresponding to the polynomial, and we call this object a truncated hemisphere. We are going to glue together this one with a copy of itself, so this would be the upper hemisphere of a sphere, and the lower hemisphere of the same sphere, it looks the same. So we've got a removed Julia's Cantor set in the upper hemisphere and the removed Cantor set in the lower hemisphere. And these yellow disks, they are gonna serve, so this is what a truncated sphere looks like. And these yellow disks, they are gonna serve as the gluings with the next spheres. What is a handle over here? Let's say we've got the sphere is 0 on the left. No, the sphere is 0 on the left, and the sphere is 1 on the right. These are glued together by just one handle. The handle goes from disks of the same size in the upper hemisphere on the left to a disk of the same size in the lower hemisphere on the right. This is how the sphere S0 is connected to the truncated sphere S2. These are two handles going from level 2 over here, level 1, let's say, or level 2, it depends on the index them, to the same corresponding level on the next sphere. And by induction, we are going to connect sphere S0 to sphere Sn using 2 to the n-1 handles going from the upper hemisphere on the left to the lower hemisphere on the right. Now, I'm going to skip this one maybe, and I'm not going to explain to you exactly how the spheres come from dynamics. But this is roughly what the Helon map does. It sends sphere S-1 to sphere S0. It sends every sphere Sn to the sphere Sn+1. The removed Cantor set in the upper hemispheres, it corresponds to the intersections of the boundary of the critical locus with the Julia set J+, but actually it corresponds just to the accessible boundary that I've told you. And on the lower, we have parts of the accessible boundary of the critical locus coming from the intersections with J-, the boundary with J-. Okay, and I would like to end this talk, first of all, by thanking you, of course, for your attention and then asking for questions and so on. And I would also like to advertise two events which are going to happen in Romania in July of next year. There is the first Balkan Mathematics Conference. It's the first edition of a regional meeting launched by the European Math Society. It's going to be on July 1st in Pitești. It's very close to Bucharest, to the capital. And it's the opening event of the 10th Congress of Romanian Mathematicians, which has lots of sections and international participation. Of course, this is the website where you can go for further information, and if you'd like to register and participate, then you're welcome to do so. Okay.
Can I have a question from far away?
Sure. Professor Minataisher.
Yeah, I just, the critical locus of the dynamical system appears in many places in nature and society. Did you ever talk, for example, neuroscientists or people in finance?
Not so much, but in mathematical finance, usually there are lots of bifurcations happening in dynamical systems. Many times when you study, let's say, mathematical finance and model them by an ODE or by another function, you can discover lots of bifurcations that also happen, let's say, in these families. In that sense, I know similarities coming from mathematical finances. Precisely about the critical lowest, it depends. For polynomial automorphisms, I don't know exactly what the proper answer is.
That's good. That's of course good, and it would be interesting to talk to neuroscientists about epilepsy, because that's also a critical problem. There's a critical locus in epilepsy, and there's also a dynamical system there. Okay, thank you very much. It was interesting.
Thank you.
Other questions or remarks or comments? Okay, thank you. No? We continue in 3 minutes.
Okay.
Colleagues, next speaker is Снежана Савуска from University St. Clement Ohridski, Bulgaria, Republic of North Macedonia.
Okay,
First talk is about mathematics and data science. Please, Snejana.
Okay, I just want to introduce that my presentation will be connected mostly with information systems and normally data science. Let me introduce my university. University St. Clement Ohridski have 10 faculty, 1 high school, 1 scientific institute, 5 associated members. We have a lot of study program, 22 in the 3rd cycle of academic study. The structure is like this. We have maybe 1,050 students enrolled by competition of this year. We have also foreign students, but the most important is that the staff we have some 380 teacher staff and 45 and 32 is women. We have a lot of people who work in this area who are the women, and we have total of about 550 people. But we have a lot of other programs. If you have to see, this is my faculty. This is the rectorate building, and the site of university is also, you can see the other information in the site. When Lichka sent me the invitation to be a speaker in this conference, I'm wondering what will be interesting for you as the mathematics, or in the area of computer science and information system, and I decided to speak for data science as the main topic related to the mathematical method that we used. And then I relate to the history of the databases. I will not show you the detail about this. You all know that the formal representation of the first databases was also mathematical formulation of the subsetter, which contain n tuples of the Cartesian product that satisfy this given relation. The sets d1, d2, dn are called the domain of the relation n, and this was some kind of mathematical representation of the relational model, which was in use all time, maybe during the 17, 18, and 19 year. The degree of the relation is the number of domain over which a relation is defined, and we defined also cardinality, which is in relation of the number of n triple in the relation. We also defined the relational attribute in the concept, which enabled the table representation of the data and of the relationship. The most important in the relational model was the definition of key in a relational model. We defined simply key or complex key, and the key was the relation R, which was connected with the attribute that satisfied the uniqueness and non-redundancy of the data. Uniqueness means that no n triple and tuple with the same key that have the same value. We introduce the redundancy, we introduce the relation. Relation can have multiple attribute collections that satisfy the definition of the key, candidate key, and unselected key in the key, which are called the alternative key, alternate key. We have to define that there is a two type of operation, mathematical operation in the relational model, relational algebra and the relational computation. For the conventional operation, we use union, intersection, difference, and Cartesian product, and for special relation operation, we use projection, selection, join, and division. And you see, it was a formal mathematical presentation and mathematical model in the relational database. But then, the data grow up, they become very large on zettabytes, exabyte, and we have many big data challenges. We have many online users. That means that complex data set and structure was very difficult, was very complex. When very instructor, they have unstructured data, and the set increased. You can see the number was like this. They have the parabolic growth, and we see that the computer world responds to create some other types of the relational model, key value, textual, and the graph, and the other solution. This data collected was collected in many formats, in many different places. They make a lot of problems. They have the very 6 V characteristic: mean, value, volume, velocity, variety, variability, veracity, and they were collected from many places, from web, from Internet of Things, Internet of Science, Internet of Medical Things, businesses, social networks, temporal, spatial data, multimedia data, digital libraries. They become more inconsistency, unpredictable. We have unpredictable growth of data. We have the data of many distributed systems, in many distributed systems in cloud, and we need a new technology tools and medical and mathematical method, which means we define the data science, which have to bring some solution for all these challenges and the problems. Arising from this new technology of big data, the data science become more desirable science because data contains science. They demand a different approach than of the classical mathematical method. They use mathematical model to fit the data to extract information. In data science, other mathematical and statistical tools are required to find fundamental principle behind the data. One of them is finding rules and property of some data sets, among data sets, to find their relationship, their connectivity, and they firstly employ statistical stances. sciences. But previously known technology as numerical analysis, graph theory, uncertainty, cellular automata also can help in this idea. And then data science as the term was coined by Cleveland in 2001 as the extension of the statistic focusing of the data science connected with data mining, artificial intelligence and statistics. But in 2009 year, the first journal of data science was announced from Columbia University, and this journal is special devoted to the application of statistical methods at large. It was 4 years ago that proposed the data science, that the data science have to extract knowledge from data, going to better understanding the data and extracting knowledge that could be science, not only limited to the rules in data sets. The next year, data science emerged into the spotlight of the science and engineering because Industry 4 demanded ability to process data sets that contain thousands of terabytes of data, exabyte required data science for extracting meaningful information and knowledge from internet-based storages and the internal storages. And now, why we use data science? First, there mentioned that from statistical and data from statistical and other existing disciplines, several important ways have to be extracted in some way. Perhaps Google search engine is the example of the power of data science. To start, they have to have the raw material, the data. This is a part of the data science, but it is intrinsically heterogeneous, unstructured. They are not only data, they are also connections with text, with images, with videos, spatial data, 3D data. Often they are emanating from network with complex relationship between the entity, and supporting this is very demanding, and supporting software tools have to include disciplinary such as science, engineering, sociology, even linguistic, in order to extract this knowledge from this data, to extract the science between this massive data set. And why we rely to the data science? We have to study many big data problems. One of them is how to extract science from data. The second one was how to extract knowledge from these massive data sets. The third one was data and data set relations. They are related in many ways. Big data processing, how to process this complex data, and then how to visualize, how to use human data interface, how to use visual data analysis, and how they have to be solved. And they were defined many of the mathematical problems in data science. There was scattered data and array-based data. Mathematically, M is a set of data points in multidimensional space or points of the array. Mathematical data space, data flows become bigger and bigger and harder to analyze. Then we find the big data solutions. We use the principal component analysis to find the primary eigenvector in data. We use the classification and into our classes with usage of k-means, neural network, support vector machine, R trees, and the other method which has the mathematical roots. Also, we have dimension reduction, manifold learning, topological structure of the data sets that all of you explore in detail. Then we have image processing, mean shift method. Image segmentation, classic and modern mathematics have contributed significantly in the past, but there is a lack of more efficient and parallel algorithm for solve this problem. There was smart search, trade-off between complexity, need of space, result accuracy, probabilistic method to avoid exponential time complexity. Also, there were recovery and reconstruction problem, which means that the vectors and the matrix use neural network to decomposition of techniques such as support SVD and PCR principal component analysis. And why mathematics in that data science? Some people used to tell this is a mathematical problem, it's not information system problem. But why this? Mathematical science, because the mathematical study number, shapes, interfaces, and everything connecting with this. But data are number, data are text, objects. The data can have shapes, can have results obtained by interfaces. But this perspective provides sense that data science is the division of mathematics. But data science is not just theory. Because mathematics in fundamental science, the theory is very good for data science, but data science is used for processing massive data, creating information and knowledge from data using mathematical method. Mathematics is used as a tool for creating all algorithm, data collection, data storage, communication between data storage, integration of this intermediate result, operationalization, visualization, but they are tools for creating algorithm in complex software tools. For these reasons, we have a lot of jobs in the decade for mathematicians connected with data science and demanded skills. Probably you have read that only the United States of America will need 1 million mathematicians to be connected for developing the software tools for data science in the next decade. They have to have some demanded skills as knowledge for big data, knowledge for using MapReduce as a tools, knowledge to use Hadoop, Spark, Cat, Apache Mahout, or capability to work with different kinds of data, XML as the language of connected data, CSV, Excel, SPSS, other statistical tools, data sampling, filtering, and transformation. This is all a part of your research as heard in these 2 days. Also, demanded skill as principal image compression, pattern recognition, data mining techniques, I will mention the mathematical background of this technique, knowledge in statistical computing using packages at MATLAB, Excel, SES, R, and Yada. Knowledge of data analysis usage of Hadoop, Zeppelin, Spark, Power BI, Tableau, and the other software tools, many of them. Knowledge in machine learning technique, neural network, genetic algorithm, fuzzy logic. Knowledge is algorithmic design technique. Just I mentioned a couple of them, divide and conquer, GREDI, dynamic programming, as the colleague from Romania mentioned. Computational method as curve fitting. Also, the knowledge about Amazon AWS system, Google's cloud, Microsoft Azure, other cloud tools will be very desirable in the next couple of years for the mathematical science. And what are the basic mathematical methods for data science that we use? We used to say search and optimization. Generally, the search is algorithm related to the graph search, not best path or object in the graph. You can use method breadth first method of graph theory. You can use, but it's not feasible for large area searching. In this search for large area, artificial intelligence can help. For decision making, we have algorithmic method, relied of the regression method, last square method, statistical method, neural network with multiple layers, decision tree for each individual step. Then for classification, we have placement of certain example into category. We have supervised, unsupervised classification. For the learning processes, we have the dynamic models of rule generation with samples to obtain the parameters of classification, training and test set of data. If the model fits to some problem, we can use it for this problem. This is the one of the biggest advance of information science, that they use the model for this. Machine learning method is such an example of this. We use graph theory. Why? Because general structure for all discrete objects, graph G, is a set of vertices and edges, and to find simply path distance between vertices, we use this algorithm from graph theory. Important algorithm for data science are breadth first search, shortest path, minimum spanning tree, and the other one. You have mathematical background for all this method. Then we use statistical method, which is also a part of mathematics science. Principal component analysis is essential technique for data analysis also. Sample of 2D data to find major data direction, regression analysis, numerical analysis, statistical computing. All this is how to find the eigenvector for covariance matrix like this, M. And this method can be extended to analyze data in n-dimensional space. Yet, this is principal component analysis. This is one of the main methods for data analysis. When we consider the classification, clustering, and pattern recognition, we have to mention that when we rely to classification, we rely to the supervised learning, known category of data points, We have some kind of pattern recognition who use nearest neighborhood methods. And when we have clustering, we have unsupervised classification where the pattern is not known. We use the k-means method. Numerical method for data reconstruction in science and engineering is used as the fitting a curve of surface, interpolation or approximation data when we use the last square method. And we have these equations, but we have to minimize the error, square error, to have the minimum of the error of the sum of all errors. And we rely on mathematical method where we have to have derivation of this function. All these mathematical methods are used to fitting a curve in our software tools to find the interpolation of approximation. And then when we speak about the design of algorithm and with some complexity, with computational complexity, we rely the concept of data structure and databases. And usually we use mathematical algorithm for data processing that not consider data structure on the data format. And we focus also of mathematical part of the algorithm. But in data science, data is stored in different place, in different format, in different structures, so they become the key of the efficient processing. And then, in order to have to be taken into account into algorithm, they have to analyze the data structure. But the data structure can be different. Can be array, queue, stack, listed, linked list, trees, some complex data structure, quad tree, octa tree, air trees. They have they can be used in geometrical data storage. They can be massive data connections and or table or array in some databases. They may contain a function, queries, relation. They have to be so different, and the database become so different, so we need a more complex mathematic tools to analyze. The difference between queues and stack, in the queue have the philosophy of first entry is removed first, the stack is the last data entries is removed first. Linked list is connection of nodes, data, and the pointer to the next node. Tree is similar as the linked list because the data pointer in the next node, they have root nodes and the data pointers. Quad tree, octa tree is used for geometrical data storage and retrieval. Image optimization with 2D and 3D is also used in this technique. And the depth at the height of the tree is calculated as the logarithm, natural logarithm of n, where n multiple n is the region of research. We also have R3, which provide query search for the geometric data analysis. Network analysis is the best way to identify the people in social networks. And you see that a big research area is connected with your research. Sofia mentioned in his presentation the NP hard problems. approximation and solution. We also have a lot of this kind of problem because the complexity of algorithm for non-deterministic polynomial time hardness problem cannot be said. So the example for this is it is a public cryptography key who have 2024 bits for encryption and usage of cloud or parallel computing to solve this problem, but it's not yet solved. Some data science problem already are the NP problem, and for this problem, which is difficult to solve, we need find some approximation of the solution to find near best answer for these NP hard problems. Let me explain some algorithm which you know probably, but it's some kind of the powerful penguin, or I don't know the name in this moment, for Google search. This is an excellent example how mathematical algorithms are used for searching. This algorithm uses deep knowledge in mathematics, not only complexity from computer science point of view, but Google search uses page ranking, and he seeks to establish a link graph and then calculate the importance of each website. The explanation is for this problem is how the page 1 have to be connected when he search, and how they have to have the page rank. The page rank is calculated from Google in this way. They start with adjacency matrix to the page 1, and this adjacency matrix is the page link graph, directed graph, which means that they are connected with page 2, page 3, page 4, and not connected with page 5. They calculate for the page 1 the page rank according to this formula. Page ranking of this page A is connected with usage of damping factor, which is probably 0.085. Damping factor, this is between 0 and 1, and usually n is a total number of pages, and the PR of TY is the page rank of the page TI connected with A. TI is a number of links going out of the page TE. And we have this formula, which you see is iteration of all mathematical method using this page factor. This algorithm run with this previous view formula iteratively, and an error limit is met. We have some error limit which is in the beginning, which is posed. We have x as a vector. We have x transpose of x, and we defined the adjacency vector m, PR x transpose, which is, and when the chi is big enough, you have this mathematical formulation. In such case, this epsilon is eigenvector of this adjacency matrix. If we add the damping factor, we get the G matrix, and the G matrix when we make eigenvector from this G matrix, we obtain this page rank for this page. This is probably one of the complex algorithms that use mathematical background to have this page rank, and it is calculated according to the needs of Google. The next algorithm which I have to mention is matching. Matching is searching for an object, and they may contain some element in a set, but this element has the structure, has element meaning, has some relation, has some connection. The good example for this is finding a substring of DNA sequence, finding a protein structure, and this is some kind of geometrical problem. Today, the most useful machine matching techniques in some kind of string matching, finding a certain substring from a big text file. And the fastest algorithm is called KPM algorithm for a random set. Search will be trivial, comparison of the element from the set one by one. When the set contains a structure, such as order, the search may use property of this structure, and if we have to consider 3D space, we have the topological structure such as composite geometric structure, such as distance method, algebraic relations such as rule, search for a valid structure of something like this. And magic could mean finding a part of this object. They found a best matching. For example, when you have the fingerprints, you have matching of couple of components who is very important to find in this way some part of matching. And then the high-dimensional search was one of the biggest problems in big data. We used the R3 for n-dimensional vector, especially for wireless networking. Related to manifold learning on cloud, we can mention subspace recovery, dimension reduction. We have to mention geometric search, especially when we have high-dimensional data search, hot topics related to data science, along with incomplete data set search, which means that you can use artificial intelligence in these cases. I mentioned that the data science mainly use statistical and artificial intelligence method to analyze data from these matrix sets in different formats and using the model. We have another data science challenges and math solution. We have to mention that method in statistics, pattern recognition, artificial intelligence, and work for local and relative small data set was okay. But then some algebraic method, including mathematical logic, we used this for find rule and format. We use topological geometric method which can find and use the property of the shapes for data sets. We use the method for meet difficulty in terms of but all this method find difficulty in coping with huge data sets. And then we rely to the connectivity. Connectivity which have to determine whether pairwise relations are linked. And then we have connectedness as a measure for degree of connectivity. And we have multiple scaling and multiple level sampling who can be used as learning and evaluation techniques. When we mention similarity measures, we rely on the lambda connectedness method. The similarity is very general for the relation, usually use the classification individual vector into different categories, and he uses K-NN method and K-mean-square method. And when geometric problem are considered, the location of information yet is involved. You have the connectivity dimension. In this moment, the connectivity become extremely important, and classification become very different from treating them as individual points. And for this moment, method for graphs, which is related to lambda connectiveness method, simply we have the pairs of G and rho, where G is the vertices, and where the potential function rho is introduced. For images, for example, G is in the two-dimensional space, and rho images is intensity function, perhaps colors of or something else. And we represent the pair for G and for this factor potential function. And we introduce the lambda connectiveness in m-dimensional real space, where the vertices is seen as the space, m-dimensional space, and we have the path connectivity, indirect path and direction, which can be calculated in this way. We use this lambda connectiveness method for decomposition, image segmentation, region growing segmentation, split and merge segmentation, data reconstruction, fitting and smoothness, maximum connectivity spanning tree, topological data analysis. All of this method is connected with this method of lambda connectivity. You have to tell me about the mathematical background, because I don't know the mathematical background of lambda connectivity. I saw something from your presentation, but this is it. More mathematical methods which we use in data science are used to solve the problem of classification and clustering. Machine learning uses automated algorithm to learn from sample of data to finding rules and making classification. First machine learning method was a regression method in statistics, but now when we have big data problems, we rely on some mathematical models, a linear equation used in regression when the regression is not linear. Data mining application request machine learning to be able to make decisions based off partitional data set and big data related method, as in data science become primary technology for using principal component analysis, KNN and K-means method. When we speak about the classification with decision tree, we have many methods which can be used for different problems. We can use neural network of GAN algorithms. Also variant learning, support vector machine, computational learning problem is related to mathematical data processing. Decision tree is one of the more desirable methods that we use, and decision tree technology does not include machine learning capability, and it has disadvantage because decision tree could be very big, and for this problem some sophisticated systems made using decision tree learning use this iterative dichotomous tree, ID3, and classification and regression tree card method as machine learning capability in decision tree. Decision tree is also associated with a very profound technological boosting with principle, which principle is to improve training in learning accuracy. The idea is to use classifier multiple times on the part of the training set to improve the strength of the classifier. It's the case of big error when we have a big error, maybe 40% in some data sets. I will just mention the neural network because it's strictly mathematical method for solving problem. The typical neural network have the input, hidden layer, output layer. Each of them consists several nodes. Most popular network is backpropagation. It is used for different type of classification problem as optical code recognition, satellite image processing. Is method which means use statistical learning, weight between nodes and adjust the minimize error in each iteration. And I will skip this because you know better than me that you have required to solve off this layer in the neural network, and when hidden layer are added, more weight metrics are involved, and the transfer function is some kind of have to be S step function with an iteration. I will also rely on some other data challenges and mathematics solution as genetic algorithms based on Darwin's survival of the fittest method, but they do not give us always the solution. The functional and variation learning, which is applied mathematics in image processing. We have optimization of a function of image segmentation. The harmonic function of this function have to satisfy that the second derivation have to be 0. And if the f is image, then we have the model which have to satisfy Memford-Shah function, which is defined in this way. This is also the mathematical problem. You have support vector machine. This method provides a separation line between the same of the boundary points of two classes, but when we have the massive set, we have rely of Cummins method and K nearest neighborhood for the initial classification, and then we have to use support vector machine. In computational learning theory, we focus on the learning algorithm for a polynomial time learnable function, and we use two major methods in computational learning: probability approximation correct learning and Vapnik-Chervenkovich theory. I don't know how we spell. they, for me, is sometimes equivalent, but you know the difference between them. For the given set of training symbols, T, we would like to guess the function fx. There x is a number of the domain x, and the guessed function is called hypothesis, and when we have the purpose is to make that the function h from x is the same as the f of x function, which is which have the small probability of errors. But you can see the other method, statistical learning algorithm, Bayesian network. We have to mention the main shift method, used to learning method, belief network, who are the sub-system of the Bayesian network. They are also Bayesian network, but they use the directed graph to represent variable and vertices and the causal information and edges, and connection that have the condition probability. The method of Bayesian network was recently used to increase the capability of MapReduce framework and Haddock, and they get the 10 time of decreasing the time for needed for some iteration. And the means shift method track a set of data points based on density function. The popular is object recognition and tracking video processing. And now, because the time is finished, for the some time I have to mention that the visual data analysis also is one of technique. They use mathematics all the time. We cannot see anything in the visual format without using some mathematical method. The data points are transformed mathematically in some visual representation, and when we want to see something visually, we rely also in mathematics. But this is a big problem. This is a problem also for data mining, and I want to see that all data representation in data science, especially also in informatics, has a mathematical base, starting from relational model to the databases. They have, they demand a solution for the problem which push the mathematician to create a new algorithm who will be embedded in some program tools, and we use it as a product, but we do not rely to the mathematics which is your idea. Thank you for your attention.
Dear colleagues, any questions or remarks or comments, please?
I have one general question, one very small question. According to your experience, for big data, what are the best methods, and depending on what? For example, for this big data set, we choose this method as the best one, and because of this, we use this method.
There is no general best method.
Yes, and that's why I ask, depending on what you choose for this or this, some main parameters of the
There is
set
a lot
of data.
of software tools that analyze data, but the problem is what you have to do. You have to do classification, clusterization, searching. We use a lot of things in the computer. Depends of the online big user, because we have many tools, which means we have a lot of different tools for different purposes. There is no such tools that is convenient for all.
Exactly. So,
Yeah, but perhaps if you have to increase the reliability of some classification, you have to find the fitting model for this classification, and maybe you can use the first time the key means method, the key nearest neighborhood, to find the primary classification, and then when the unlinearity is arrived, you can use the segmentation of nearest neighborhood or something else, depends of the problem that you have to solve. You have a lot of different tools, a lot of different methods that are used, but we usually do not know what method is behind these software tools. I don't know. I use Veka for data mining, but the Veka has 20 types of possibility. If I use perhaps for classification, I use one method. If I use it for clusterization, I use the unsupervised method for neural network, or I can have a tree e-card of card method, some of them. There is a lot of methods. We didn't know which method are behind this. This method of searching in Google Tree was researched by our student, and we know how it works mathematically. But they all time they change the algorithm. But the main search is with page ranking. The main algorithm in this. But they in the level of the little of the some parts of the calculation, they maybe use nearest neighborhood, or they use some maybe support vector machine. I don't know, because these algorithms are embedded in the software and they are closed because they sell this product, and they do not open the source code to find what method they are used. But they use the mathematical method. It's obviously that everything behind is mathematics.
Thank you. Any other question? Please.
The Google page rank algorithm is of course a trade secret, everybody knows it, but on the theoretical level, I wanted to point out that it's actually a dynamical system. So
Yes.
the space is not a complex space, it's a space of probabilistic vectors. The matrix, which is the function of the transition matrix, every application of the transition matrix is like an iteration. It's the iteration of the function. And it converges to the unique probabilistic eigenvector of the eigenvalue 1. But when you solve a matrix and you do mv equals v, it's like a fixed point for a function. So it's converging to an attracting fixed point in an appropriate space.
Yes.
Hence, dynamical systems are everywhere.
Yes, it's dynamical system, which means that they renew the information in every 5 seconds, I think.
Exactly. It's very complex in itself. It's a big data problem, so hence the complications in it.
But this is the power of mathematics that can translate in parallel computing. They have solved this complex and
the map reduces.
Yes. There is no one method used for something. We all the time we rely on the better method, and when something have the new solution, they probably will be on the data science something of on the web, we can see, and we can and the company who make these tools will probably embed this method instead some of the other one.
Thank you. Other questions? It's coffee break time now.
See, my officer will come. Oh, I see.
to the last session because we have had to do another job. So let us not be late. So it's a pleasure to run the last session. We have two talks, and the first talk will be by Professor Bulgaria. She is colleague of our institute and also in the University of Constance. So you see the title, Machine Learning Approaches to the Debugging of Quantum Computers. So please, you have the floor.
Thank you very much. I'm a doctor, theater professor. I'm not sure if I'll ever become a professor. Yeah, so thank you very much. Thank you very much for attending my talk. So first I will discuss, I'll define a few concepts that are necessary to follow the talk. Mainly I will discuss what is quantum state tomography in the setting of a quantum computer, what is important, what means a quantum, what defines an efficient quantum state tomography, how it can be defined as an optimization problem. Then I will discuss what means optimal quantum state tomography in different settings. And then I'll discuss a special case for optimizing quantum state tomography. And we'll also, these are all ideal scenarios, but then I'll discuss about, describe optimal quantum state tomography for a noisy device, for existing quantum computer. So the first thing to define is for when we talk about quantum computing is the qubit, the notion of qubit. Qubit is the quantum version of a bit, and it can be the state of a qubit can be defined by the block sphere. So any point on the block sphere can describe a state of a qubit. There are many different physical implementations of a qubit, but of course physicists care about that. I, as a computer scientist, or perhaps you as mathematicians, maybe don't care so much about what is the physical description of a physical implementation of a qubit. It can be described in a photonic way or through a spin of an electron. There are two basis states, 0 and 1, and then the state of the qubit is defined as a linear combination and is anywhere on the sphere. And the mixed states are inside the block sphere. So these are pure states and mixed states here. The qubits, as I said already, are building block for the quantum computers. We have superconducting, different types of architecture, superconducting qubits, spin qubits in semiconductors, nuclear spins in atoms and molecules, and nitrogen vacancy centers in diamonds. This is often used for sensing, for the so-called quantum sensing that is used in very top-notch medical devices, for example. I'm paying slightly bit more attention to this because this will come up in the application of a certain method. So one of the most important aspects of the quantum computer, or what drives the computational power, potential computational power of the quantum computer, or an important property is the entanglement. Given that we have already a composite system, this is defined by the Hamiltonian HR and HB of mainly two qubits with these bases, that we have product states that are defined as products of elements from the first subsystem and the second subsystem, for the first qubit and the second qubit, the subsystem of the first qubit and the second qubit, and everything else that is not a product state is an entangling state. It's a very classical example of non-product states or namely entangled states of a two-qubit system. It's called the Bell states. For the quantum computer, you really need that you really need this high entanglement for the quantum computer to function properly. They cannot always achieve it. It's problematic to achieve this in reality, but nearly all states in a functioning quantum computer are entangled. So the third very important notion is the notion of quantum gates. The quantum gate is nothing but a unitary operation that is applied to a qubit, and it is a change in the state due to time evolution. So there is a requirement to have a universal set of qubit gates. And a very important result is that only with single and two qubit gates you already can have a universal set that you can represent any. Universal set means that you can represent any gate, and you can represent any gate only through single and two qubit gates. These are a sufficient set. This is of course very important for the implementation of a quantum computer. For example, if you have one universal two-qubit gate and only single qubit gates, you already can have this universal. This already constitutes a universal set. A single qubit gate. These are different types of rotations on the block sphere. So two independent axes are needed to perform each desired rotation, and this is already. Any single qubit gate can be presented through two axis, or even a single axis, but mostly two axis rotations on the block sphere. And an important gate is the Hadamard gate. Again, described only as a unitary matrix. So the two qubit gates, they involve, as the name suggests, two qubits. So this is the basis, and these are some classical examples of a two qubit gate: the swap gate, the C0, and the square root of swap. They are again are applied to a qubit, and the result is a different state of the qubit, or to two qubits, sorry, and the result is different state of the two qubit system. Nearly all two qubit gates are universal, with the exception of the swap gate. So very classically, C0 is used for the implementation of a quantum computer. The main idea about the main importance of why do we want to use a quantum computer? Perhaps you have all heard about the term quantum supremacy, which now they're trying to not use as it's not considered to be politically correct, and they're trying to utilize to popularize other terms. But I'm still using quantum supremacy because it seems to be the most established. So quantum supremacy, this is the demonstration or the property of quantum computer performing provably better than a classical computer. So there exists a small set of problems for which quantum supremacy is already shown. So we all somehow think, or it's somehow always considered that we want quantum computer because it's more powerful than a classical computer. But in fact, this has been demonstrated for a very small set of problems. Most of the problems for which it has been demonstrated are very artificial examples that have been specifically designed to demonstrate quantum supremacy, and with a lot of conditions. But the two most important and not so artificial examples are Shor's algorithm and Grover algorithm. The Shor's algorithm is focused on factorization, and it has a classical part and quantum part, and the quantum part determines a period of a function using quantum Fourier transform. And classically, it scales exponentially, and here it scales polynomially. So this is one of the very few natural examples where it has been proven by Peter Shor, the quantum supremacy has been really demonstrated and proven. The other is the Grover algorithm, which is focused on a search, which is trying to solve the problem of a search in a non-ordered database. My work, or this is the work that is, I'll show in the end, but this is the work between Niklas Rolling and Professor Burkhardt, but it has been focused on quantum state tomography, which is one part of the functionality, one important part of the functionality of a quantum computer. The goal of quantum state tomography is to determine the state of a quantum system. The state is always represented by a density matrix. So density matrix describes the state of a quantum computer or a system of qubits. And it provides full information of the state of quantum computer. And this is important for when you initialize a system, for example, and you need to know if you have initialized it correctly. You need to test it and perform quantum state tomography in order to really see the correct state, if it's in the correct state. So it is from the tomographic approaches, this is the least efficient and the most informative approach. It is considered the golden standard for the so-called methods of verification and validation. For a d-dimensional system, the goal is to estimate the density matrix of a density matrix that describes the state of a system. It works in the following way: you have n copies of the system, and you perform measurements on these copies, and then through a procedure called reconstruction, you estimate the state. And so far, most of the work on improving, so it is very provides the full information of the system. It's a very powerful method, but it is extremely inefficient. And so far, the focus mostly has been on improving the reconstruction, this reconstruction phase. This is a very statistical phase where using maximum likelihood or more sophisticated, initially maximum likelihood approaches, but nowadays more sophisticated machine learning and other statistical approaches to improve the efficiency of this part of the quantum state tomography. As I said, is quantum state tomography feasible? Performing quantum state tomography on a 50-qubit or even smaller quantum computer, it is not feasible. On the other hand, elementary quantum gates are single and two, as we said, single and 2-qubit gates. So we can perform in parallel quantum tomography in smaller subspaces. Still, the quantum state tomography itself may need to be more efficient even for smaller systems. So our focus is to optimize quantum state tomography, but in a different way. We want to, just go back to show you on the picture, we want to need here less numbers of copies. So to perform minimal number of repetitions of measurements in order to grasp the full information of the system. So when we talk about optimal quantum state tomography, we talk about optimality in distance. So the problem in setting is the follows: we are given many instances of a state, and you have measurement. You do measurements using different operators, and given a fixed precision, you want to minimize the number of measurements on the system, so the number of experimental runs. And this can be formulated as an optimization problem where you're trying to find the quorum of measurements so that they are defined as projectors on the state space. So you want to you want to find such a quorum, such a set of projectors that gives you the most information, and you minimize the number of necessary runs. So the quality measure for this optimization problem is information-based. So you want to maximize the amount of information that you gain. You want to use such projectors that you maximize the information that you are obtaining from the measurements. This is an optimization problem of high dimensionality, and this is just some, how to say, schematic representation of a very complicated, let us say, high-dimensional search space, and you are searching here through different methods in order to find this optimum that is an information-based optimum. So, I'm going to talk in a bit more detail later on to explain these notions. I just want to give you here the very basics. So we are going to be considering two types of measurement operators. One in a Hilbert space of dimension n, which is the size of the system. And the other will be the degenerate measurements, which are in Hilbert space of dimension m, which is n minus to the large n. So this is here you're projecting on subspaces. So the quality measure in this is not our result. I'm going to give more details, but in certain situations for certain n's, the quality, the optimal measurement is known. The optimal measurement state of measurement operators is known. This for prime power. No, actually, for a full set of n+1 mutually unbiased bases, which are used as measurement bases, are known to be optimal. I'm going to now just give you intuition. Mutually unbiased bases are such measurements that if you measure along one basis, you get zero information from the measurement that will help you to measure in the other basis. So they're somehow informationally detached, so like roughly speaking. And the problem is that they are known to exist only for prime power. They don't exist only for prime power dimension, and they're hypothesized. It's hypothesized that they don't exist for non-prime power dimension. So for Hilbert space, so quantum system that has a dimension of the Hilbert space non-prime power dimension, such a set is not known to exist. For example, for dimension 6, only a set of 3 and mutually unbiased basis is known. The quality measure that is used to evaluate the optimality is in fact a parallelepiped. So the volume that is spent between the projectors. So you want, in order to maximize the information gain, you want your projectors to be spending maximal volume. And in this case, of a single qubit case, the optimum will be described by the axes, and this parallelepiped is the volume, because you can see that anything else will be leading to a smaller volume. To describe things in greater detail, the problem can be defined as follows. You're given many instances of the same state in a quantum system of a dimension n, and we perform many measurements on this state using different measurement bases. And the question is how to choose bases so that we learn the state with maximum precision. With a fixed precision. So we want a fixed precision. For a fixed precision, we want to have a minimum number of runs. And this can be, as I said, formulated as an optimization problem. We want to find the optimal form of projectors or set of projectors which minimizes the number of experimental runs. And as I said, this is an information-based quality measure. And the answer of this, what are the projection operators that maximize this information-based criteria? This depends on the setting of the quantum system, namely the dimensions of the Hilbert space, the type of measurements, whether they're degenerate or non-degenerate, and this type of measurements, if it's a von Neumann measurement versus a POVM. And two So we will consider two cases. The one is measurements only within the given space that describes the quantum system. These are called von Neumann measurements. And the other is to allow measurements in larger space, which is the generalized measurements, the so-called POVMs. So for the non-degenerate measurements, non-degenerate projective measurements, as we said, the optimum, in certain cases it is known, and it is the n+1 mutually unbiased basis, which are used in the measurement basis. And a set of orthonormal basis in CN is mutually unbiased if any two basis vectors Нещо не натискам като хората.
Не, просто се разпадна връзка и след това се възстанови. Сега ще стане така.
That fulfill any two set of basis vectors from different bases. So, for if any two sets of vectors from the different bases fulfill this equation. No more than n+1 such bases exist in Hilbert space of dimension n, and it is for sure known to exist only for prime power dimension. It can be constructed. It is known how to construct it, so it is an open question whether or not it exists for a dimension which is not a prime power dimension. And if a set of n+1 mutually unbiased bases does not exist, then what is the number of mutually unbiased bases that exist for any given dimension? These are open questions. This is not known. So the second case is a measurement in a larger space. It is a more generalized type of measurement that is described by a set of positive semi-definite operators, and they're called, in the general case, POVM, so positive operator value measurement, and in a very special case with very nice properties, they're called SIG POVMs, which are symmetric informationally complete POVMs. The solution to optimal quantum state tomography is also shown that in a more general setting it can be described if such a SIG POVM exists. It also describes a set of measurement bases or projection operators which are given optimal solution. So a set of n square unit vectors form a SIG POVM if any of these two vectors fulfill this equality. And here is an example for Hilbert space of dimension 2. This is this regular tetrahedron that is described by these equations. And the Zauner conjecture is that SIG POVMs exist in the Hilbert spaces for any finite dimension, but this is proven only up to n equal to 151. So now I'll just very briefly describe a notion that is related. We will show how it's related to the optimal measurement basis. So this it is based on block designs, so combinatorial designs. The problem of combinatorial designs deals with how to arrange a finite set. The problem is given V elements, which must be arranged into B blocks, where each block contains K elements, and each element is in exactly R blocks, and each 2 or T elements are both contained in lambda blocks. So for which quantuples such design can be constructed and how. This is a combinatorial problem. This is an example. For example, for v equals 7, b equals 7, k equals 3, r equals 3, lambda equals 1. This is such for these defined parameters. This is such an example of where you are arranging the elements. So a design that is directly related to the block designs are so-called quantum designs. They're again investigated by Zoyner, and there is a correspondence between block design and quantum design. So where V is the number of elements, to this V corresponds here orthonormal basis in dimension V. Here B is the number of blocks. Here B is the orthogonal projections for these quantum designs. In the block design, key elements, you want key elements in each block. Here you want each projection to be a projection in k-dimensional subspace. And here you want each element to be in R blocks. And here you want each basis vector to be in R projective spaces. Here you want lambda to be the number of blocks that contain any two elements, and this can be generalized to T. So this is for two designs, but the general definition is for so-called T designs. And here you want each intersection, the corresponding parameter would be that each intersection of two subspaces has dimension lambda. This is the notion of quantum T design, for which lambda is T, and intuitively we have that the Haar measure, translation invariant probability measure, is equal to uniform probability distribution over all quantum states. And the set of quantum states, so that you want the set of quantum states to be indistinguishable from the perspective of Haar measure given T copies of the state, of the quantum state. And formally, this is the definition. This is the definition of quantum T design. The quantum design is a set of projection operators in dimension V, Hilbert space of dimension V, and it is regular. It's called regular if there is such if and only if there is such K, for which the traces of these operators is equal K for all the projectors. This degree S is the number of elements in the set. And the mutually unbiased basis and the SIG POVMs are quantum designs and can be looked upon as quantum designs, and then the properties of quantum designs can be used to infer properties for NUVs and the SIG POVMs. So basically, NUVs and SIG POVMs are complex projective two designs. And for them, the known Welch inequalities hold. And there is an important result that quantum two designs are optimal for quantum state tomography. So these are already published work that deals with quantum two designs for optimal quantum state tomography, exactly in the sense of how we define optimal quantum state tomography. So in the type that you measure in the most informationally gaining way. So all these works consider different scenarios. Basically, they can be defined. Two main cases can be considered. Which have been investigated and for which results exist. One is quantum state tomography, where you are measuring one qubit in a composite system. The Hilbert space is of dimension n, then the rank of the projectors is n over 2, and you need n squared minus 1 of these projectors to form a quorum, a set of projectors. So this is the number of projection operators that it is known you need. And the ideal scenario, so which projectors operators you need the projection operators for which the subspaces which are projected on by these operators are mutually unbiased, namely the traces of the products is this. Then the traceless parts would be orthogonal to each other. So basically the important part is that the optimal situation is such projectors for which the traceless parts of these projectors are orthogonal to each other. Yes, so this is a result by Botman and Haas, where given they find a solution for measuring 1 out of n qubits, but in a case for p co-prime, where the dimension of the Hilbert space is again p prime. P to some power where p is prime. The quorum then consists of n squared minus 1 mutually unbiased subspaces. So this is a generalized notion of the mutually unbiased basis. These mutually unbiased subspaces, they are half-dimensional in this case because this is the rank of your projection operators, and they show how such mutually unbiased subspaces can be constructed. You need 2 ingredients, so you need complete sets of MUBs, and then you need so-called Johnson codes. But here you can see already the problem. So the construction in this scenario requires the existence of MUBs, which are also known to exist. That's why the result is again for a prime power dimension, because you need their proof is constructive and they need the full sets of MUBs, which are so far also possible to construct only for these dimensions. So the resulting QST quorum, so the set of projectors, can be after that extended to obtain maximum orthoplectic set. So this is a set that fulfills the orthoplectic bound. And this set, the extended set, is a quantum to design. So the orthoplectic bound is so maximum orthoplectic set is a set which maximizes the minimal distance between the, in this case, the projectors. However, it is not what to do in a situation where you don't have a prime power dimension. So the smallest number, the smallest quantum system for which is not a prime power dimension is a qubit Q-tree system. You see already that here you don't, that any qubit system is a prime power dimension. The Hilbert space describing any qubit system is a prime power, has a prime power dimension, but for a qubit Q-tree system, the dimension is 4. And this describes this nitrogen vacancy center in a diamond that I said that is heavily used in sensing. This is the physical representation. However, from schematic representation, it can be shown as this. So you have a qubit. This is the qubit. This is the qubit, and the measurement is on the qubit. So you have a 6-dimensional system, but you are measuring on the qubit. You have a Hilbert space of dimension 6, and since you're measuring on the qubit, the rank of the projection operators is 3. At 6 over 2. And then the size of the quorum that you need, so the number of projection operators that you need is n squared minus 1, 35 projectors of rank 3. And the measurement is consists of elementary measurement plus unitary operation. In this case, as we discussed, this construction of Botman and Haas that uses the Johnson code and the MUBs does not work because of the non-existent, because the full set of MBs is not known. And the question that we pose to ourselves, what is the optimal quantum state tomography scheme in such a situation when you don't have a prime power dimension, and how to find it? So we approached it in the most boring way as an numerical optimization problem. We used the quality measure that was used by both for the Wouters and Fields in the MUB's result, and by Botman and Haas for the mutually unbiased subspaces that I already said maximizes the volume spent by the traceless parts of the projection operators. And we parameterize the projection operators, and we get 612 parameters, which is relatively high but not super high dimension. And the idea is that the ideal volume would be the ideal volume would be, if it exists, such that the projectors project on mutually unbiased subspaces. So the traceless parts of the traceless part should be orthogonal. So is this theoretical idea reachable? So this is somehow very simplistic two-dimensional projection of the search space. We used, in this case, different numerical approaches, including reinforcement learning as an optimization approach. Reinforcement learning is an approach in machine learning that is suitable for optimization problems. It is defined as an agent communicating with the environment, and as it communicates with the environment, it gets an observation, it performs an action, and for this action it gets a reward. And from this reward, it learns the proper actions based on the environment that it is in. And this can be said to be used for optimization problems because at each step you are learning what your strategy should be in order to maximize your reward. In our case, we define it as follows. Our environment consists of possible values of the 600 meaningful values, so intervals for each 612 parameters, and the reward, as we said, this is our quality measure, the volume spent by the traceless parts of the projection operators. And at each step in our environment here is local heuristic, so you don't just walk and change randomly as it would be, I don't know, standardly done, that you change these values of the parameters. This is a continuous environmental space, but you perform local heuristic at each step, and then the log optimum that you're getting is your reward. This we have done because this just leads to much better result. Now you need much fewer steps to converge. Basically, now I'm going to discuss how we approximated the ideal quantum. So to disclose, the ideal quantum state tomography quorum does exist in dimension 6. And we use reinforcement learning as a numerical approach using local optimization approach. In this case, the Powell method was our local optimization approach. And our conjecture, because after playing with I'm going to say the data, but after playing with this problem, we already could sense that the ideal quorum would be reachable. And that's why after getting relatively close to the ideal solution, we started alternating, maximizing the volume spent by the traceless parts of the projectors and minimizing the non-orthogonal contribution. So this is already, since we somehow can sense that they should be orthogonal to each other and that the ideal case will be reachable, the optimal solution in fact is the ideal solution. That is why we minimize the non-orthogonal contribution in order to improve actual convergence. And we converge to the optimal solution, to the ideal quorum, in some 10 to the minus 4 order of magnitude, which is from physical point of view irrelevant. As a consequence, we approximated a complete set of mutually unbiased subspaces. So this was for dimension 6. Which is a previously unknown result, and based on the Botman and Haas construction, we we additionally constructed a maximum autoplex bound achieving set of the subspaces if we also include not only the projector speed j but also 1 minus speed j, which is also previously unknown for dimension 6, that there is a maximally autoplex bound achieving set of subspaces. So the general idea, what we wanted to accomplish is optimal customized quantum state tomography that, given different specifications, different dimensions of the Hilbert space that describes the quantum system, so different size of quantum system, different types of measurements, different rank of the projection operators or rank of measurement, different types of noise, and given different types of analytical machine learning approaches, you always get as an output the efficient and the best quantum state tomography scheme that you need for your specific description. So the idea was that you input specifications of your system, and then you do some parameterization, formulation, numerics, machine learning approaches, and so on, and as an output you get customized optimal state of projection operators. However, for us it was very important that I don't know if it was very important, it is required to investigate optimal quantum state tomography in the presence of noise, because probably most of you know that the existing quantum devices, they're the so-called noisy devices, which are heavily affected by noise. So for us it was very important, all these scenarios that we so far discussed are ideal scenarios which do not take noise into consideration. And they are not applicable for the current small and very noisy devices. I mean, from small they're of course applicable, but for noisy they're not. And our main considerations to do quantum state tomography in the presence of noise was what kind of noise model is appropriate, and how does the noise affect the quality measure, because this is the stepping stone on choosing, finding through some type of numerics optimal projections that you need an appropriate, meaningful quality measure to evaluate the set of projection operators. And before we saw that this is the volume that is spent by the projection operators, and here how does the noise model chosen affect the volume spent, or how should we modify the quality measure. Of course, this was a very first work. Ideally, you shouldn't do noise model here, but your noise model should be based on noise characterization that is directly inferred from a quantum device. But we started simple with already preconceived noise models that are based on some theoretical considerations. And we consider two types of noises that are common in quantum computing. One is the polarizing noise, and the other one is over and under rotation. The polarizing noise affects the full system, and the over and under rotation affects the angle of rotation of the gate. And we consider two types of interaction, Heisenberg interaction between the two qubits and Ising interaction. So we assumed noise only on the 2-qubit gate. We disregarded the noise on single qubit gates, because the noise on the single qubit also read out errors and other errors, because the noise on the single qubit gate as well as the read out error can be mitigated. So we only consider 2-qubit gate noise model. So the most important is how to modify, as I said, the quality measure. And we calculated that the quality measure under noise would be the following expression. So the original quality measure multiplied by a product of Qi, where Qi is the probability with which you correctly measure the measurement, the correct measurement, the correct outcome for a measurement. So basically, the influence of noise. The problem with the noise is that different measurements are affected in different ways, and the average information gain depends on the measurement. So basically, we assume a simple case for the depolarizing channel, for the overnight rotation it was slightly different, but for the depolarizing channel we assume that you perform correctly measurement with probability Qj and random outcome with the probability of 1 minus Qj. And then our modified quality measure would look like following expression. And here S was numerically calculated to be we considered a small system of 2 qubits, so the dimension of the Hilbert space is 4. And we numerically inferred this degree to be 2.4, this numerical result. So basically this represents a shrinking, so this is a shrinking here of the parallelepiped, and this parallelepiped here is no longer the optimal, or may no longer be the optimal solution under the influence of noise. So basically, then we started with the following measurements. So this full sequence of gates, of swap gates and unitary operations. This is a universal gate, and here is our measurement. And we started first with the numerical approaches. That try to maximize our where we try to maximize our new modified quality measure. Again, we parameterize each gate sequence. This is the gate sequence. So these are the swap alpha gates, where alpha defines the time on which this gate is switched on. This is as I showed you in the beginning, this is a 2-qubit gate. And we applied different approaches here for this some type of preliminary exploration. So we applied a combination between global approaches such as simulated annealing and then local approaches for convergence to already good points in order to really locate good solutions. And then we discovered, so this is the plots for different entangling time alpha, so for the different times where you switch on this gate, we find different optimized quality measure. So this is for different levels of noise. So basically what we find for the optimal solutions, which we optimized, I cannot say optimal because this is a numerical result, for the optimized solutions that we found, what we discovered was that each optimized solution varies from the NUBs only for the amount, this mutually unbiased basis, only for the amount of switched on entangling times. And then we decided a different approach after we did the brute exploration, brute force exploration, and we looked at the results, we decided to then investigate local optimization approaches with standard MUBs, mutually unbiased subspaces, as starting points. And then we discovered that the optimized solutions that we find differ from the MUBs only based on the entangling times. And the most important result that we found is that currently, since such analysis has not been performed, only measurements that project on product states are used. This is so-called non-separable basis. They're separable because they project on product basis, on product states. And we show first with our noise model, we show that using entangling projection operators on entangling states, so the so-called entangling gates, there is an advantage for realistic noise levels. And the already known NUBs, the NUBs are already better than what is currently used in experiments. Additionally, we did so-called gate sequence optimization, where we allowed for a sequence of gates to be repeated and find the optimal length of the sequences that would bring, again using reinforcement learning, that would bring the best result in terms of the quality measure, namely the information gained. And we got a lot of criticisms for our work that our noise model may not correspond well, may not perform well on an actual quantum device. since we haven't done the so-called noise characterization. Noise characterization is when you don't use theoretical considerations to design your noise to your models, but you directly extract it from the noise for a particular device. So this, we got criticisms for our noise model, and that is why we decided to run our and do a validation on an actual quantum device. So we performed to show our main results, which is the benefits of using integrated gates versus only project measurements that project only on product basis. We ran both on actual IBM quantum device. So only for a 2-qubit, only on 2 qubits. So it was a 5-qubit very small quantum device, but we ran for our 2-qubit system, and we again demonstrated that. So this is so up to a certain point. So the greens are the mutually unbiased bases. They are always better up to a certain point, and then it converges. Here there is a separation which is based on a systemic error, but in fact here is already somehow the difference is too small. So for important scenarios, indeed there is a benefit for using mutually unbiased basis, which is what we also discovered numerically. So thank you very much for your attention. This talk was based on 2 works by me, Niklas Rolling, and Professor Burkhardt.
Thank you. I would ask you if only short questions and remarks. So, if not, so thank you again. We will directly continue with the next talk, but before be informed that for foreign guests we have ordered some taxis for the concert, and Vilichka will tell you. So she is a coordinator of our bilateral project between Bulgarian Academy of Sciences and Serbian Academy of Sciences and Art, and working in the field we have here group. So you see the title, solving some fractional partial differential equation by using theories of semi-groups of operations. Please.
Thank you. So someone has to be the last speaker. Okay, it has some advantages. I think no one will complain if I finish earlier. Yeah, at the beginning of my talk, I would like to thank the organizers, especially to Velichka, and also to my friends, Professor Virginia and Branka, first for inviting me here to participate to this conference, And then for great organization and for great hospitality, I mean that we all feel very, very welcomed here. And I have to admit that the colleagues of mine from Novi Sad who used to come here, well, they were jealous when they heard that I again advised that I will again come to Bulgaria and Sofia. Because they knew that I would have a great time beside working. Yes, thank you very much. The good things about conferences like this is that it gathers mathematicians from many different fields. So my topic will differ from many other topics. So I will speak about partial differential equations and some specific that involves fractional derivatives, and again with some specific methods of solving these partial differential equations. As Professor Virginia said in her introduction, I come from the University of Novi Sad. I teach at Faculty of Sciences at the Department of Mathematics and Statistics. I teach probability on bachelor level of studies and also stochastic analysis and operator theory for master students. But my scientific field of interest is mathematical analysis and particularly partial differential equations, both deterministic and stochastic, and in the last 10 years also fractional partial differential equations. So, as you will see, the method that we are going to use here is complex in a way that it mixes many different, sub-area of mathematical analysis, and I will try not to go into the details, but I would just like to give you some basic idea of what am I doing and how do we try to consider the problems that we are interested in. First of all, as I said, for the last 10 years, I became very interested in fractional calculus, although I am still considering some differential equations which are not involving fractional derivatives. But fractional calculus is something that I find very interesting, and I find it very good because it is proven to be very useful, especially when one should model some real-life problems that include memory effect issues. And therefore, I somehow realized that some problems that I have considered earlier, it would be nice if I could consider from the fractional point of view. Also, I have to admit that it helped me a lot that there is a group of people at my faculty, at my department, who works very seriously in this theory and who helped me a lot, who introduced me to the theory, and therefore I did not have a very hard task. We can discuss about the application of fractional calculus, but I think that today it is really clear that the application is really widespread in many different areas. Here I mentioned some of them. Of course, they came from mechanics and physics at the beginning, and engineering. But also researchers today use fractional calculus in many other scientific areas. And I mentioned here also fluid mechanics, electromagnetics, electrochemistry, optics. And recently, colleagues of mine, for instance, work a lot of application of fractional derivatives in medicine. For instance, fractional derivatives are very good for modeling viscoelastic materials. And for instance, our brain and many other tissues of our organs in human body, maybe not only human, are viscoelastic. So many processes that are going on in human body could be also described not only with differential equations that include integral derivatives, but sometimes even better, which has been proven, with fractional derivatives. So we have a group of people who are very interested in modeling in medicine, modeling by using fractional derivatives. I myself also have started to consider this epidemiology model with using fractional derivatives, especially because this memory effect, which could be very useful in this story. So I will not show you results here because I don't have something which is worth of mentioning because I have already started. Maybe COVID just started me to think about it. But let us hope that soon I will have some results in that field too. As you will see, here we will consider the partial differential equations which are nonlinear. When you have nonlinear equations, then you usually face problems because many of nonlinear partial differential equations are not solvable, neither classically, because they don't have a classical solution, nor even distributionally. I mean, in a general sense, in the sense of using Schwarz distributions, because, as you know, nonlinear problems often includes multiplication, and multiplication is not well defined in the set of Schwarz distribution. So you have to find some more general, in some sense, space of functions where you can consider your problem, but of course you have to connect your initial problem with that space of general functions. So that is something that we are going to do here. But if not that, then some other authors use many, for instance, numerical methods for solving fractional equations, because very rarely you will see that you have an analytical solution, that you have some solution which, okay, it's great, it solves the equation. So many authors simply try to find a way to solve the fractional equations, and some of these methods which are listed here works, and I myself do not use them because I use this other approach that I will show you here, but these are possibilities, and you can find many papers dealing with such methods here. Our method is a little bit different. So as you will see, we start with a problem with a partial differential equation, whatever it is, with fractional derivatives. We write it in an operator form, and then instead of this original equation, we consider an approximate problem. I will show you in what way we are making this approximation. By using semi-group of operators, by using that theory, we solve that approximate problems. But then, of course, we have to connect somehow this approximate problem with our original problem, and we do that by showing that these that two operators, non-regularized and regularized one, are associated, L2-associated, which is good enough in the spaces that we are using. And not only that operators are associated with, but in most of the cases that we discover, that we consider, solutions are associated as well. And now you can ask if you have solution of the original problem, why do you approximate at all your problem and do such a thing? Of course, we simply suppose that if our original problem has a solution, then it is we show that it is associated with our approximate, and this gives us the courage to carry on with our procedure when our procedure is good enough, and we believe that the solution of the equations which do not have classical solution is also, our solution is also very good, because when in case that it has solution, these two solutions are close enough. Okay. So, for instance, I will show you some kind of equations that we are working, we were working with and still we are working with. And later I will show you the method, briefly show you the method, how we work. For instance, fractional evolution equations with variable coefficients. These equations can be written in the following form. You see, I already wrote it in operator form. Here we have operator. Later I'll say something more about the operator A. What is usual? I mean, there are many types of fractional derivatives, but we, at least I, use these Caputo fractional derivatives, then Riemann fractional derivatives, and in my work also Ries fractional derivatives. I will show you definitions of all of them. But Caputo fractional derivatives is used here, you see from the left-hand side in Cauchy problem, because it is very good because it allows to incorporate the usual initial data and boundary data, and also it's good because the derivative of constant is zero. So from the left-hand side we put here Caputo fractional derivative, whatever it is, and fractional derivative, I didn't say that, but I suppose that you know. I mean, it allows the derivative of order which is not integer, but it's any real number in general. So here we, sorry, I wanted to press pointer button. Here we take alpha to be between 0 and 2. Then, of course, this second initial condition here, it stands only in the case that alpha is especially in between 1 and 2. We work everything in infinite domain, and we consider several different cases where operator admits both integer or fractional order space derivatives with variable coefficients which depend on x. And by changing operator A, we can obtain the different types of equations: time inhomogeneous fractional diffusion equations, time-space inhomogeneous fractional diffusion equations, fractional reaction-attraction diffusion equations, wave equation, heat equation. So simply by changing this alpha and by changing the derivatives, as I will show you in this operator A. So, for instance, here we consider space fractional reaction-attraction diffusion equation. These equations are considered by many authors because they have many applications. Here we took, as you see, this is only fractional with respect to space. It could be, of course, and we consider that case when it's fractional with respect to time too. But here I choose to show you on this case. And these derivatives that are appearing on the right-hand side, they are space fractional derivatives. First one is of order alpha, which is in between 0 and 1, and the other one in between 1 and 2. And we take these derivatives to be left through the fractional derivative, whatever it is again at this moment, but it can be some other type of derivatives like right, Liouville, or Ries fractional derivative. Of course, if you specially take alpha to be equal to 1 and beta equals 2, then you will obtain the classical reaction-attraction diffusion equation. Here I didn't include these cases because I want to consider the fractional case. Okay, and what about these coefficients? These coefficients K alpha and K beta, they, in this equation, For example, I can consider the case when use load concentration, and in that case, K alpha and K beta can represent average fluid velocity and the dispersion coefficient, respectively. And this F, let me show you back the slide, previous slide, this F is actually a source function. If I consider this a load concentration, that it will be some kind of contaminant source, which is common, for instance, in hydrogeological phenomena. I listed here some other possibilities where to use the equation like this, but I think that I will not have time to go into the details. For instance, maybe just to mention that one can also consider the transport of transport equation, actually the transport of a chemical or biological tracer carried by water through a medium which is uniform, and the equation that describes that transport is of the type above. And this is very popular today because of this pollution and everything that is going on in the, I don't know whether everywhere, but in Serbia definitely we are facing that kind of problems. Maybe just to mention that different authors use different terminology in describing some phenomena that appear here. For instance, many authors, instead of advection, they say convection. Instead of diffusion, they use term dispersion. So therefore, you can find many other names for the equation that we consider here. So it could be reaction, advection, dispersion, or whatever it is. And since this F is a source, then you can use the term convection, diffusion equation with sources, whatever. I mean, I just put it here in case that you had a chance to see some of them equations, but they are called differently. Okay. And of course, by putting some of these coefficients to be zero, then, for instance, if you put K beta to be zero, then you obtain only reaction advection equation. But similarly, if you put if you put K alpha to be zero, then you will obtain reaction diffusion or reaction dispersion equations. Both of them have math implication. For instance, I wrote here that the other one, where K alpha is equal to zero, it can be used in population biology, so it could model the spread of invasive species. Okay, I will not go into the details because I don't have time for that. Okay, and another type of equation that we have also considered is time fractional wave equation and time-space fractional wave equation, which is given in the following form. And again, from the left-hand side, we have this Caputo fractional derivative, which I explained that is used in Cauchy problems. And from the right-hand side, we can choose, but we decided to take right-hand fractional derivative. And I will not talk about this equation. I will choose to talk about heat equation, and especially I will consider stochastic heat equation. So, as you see, this is the equation of the following form, as in the slide. So we have here, in this equation, we have this K of Tx, which is the term called thermal conductivity. And of course we have derivative, which we will choose to be so-called raised fractional derivative. We have this source function, and we added here this stochastic term, and this P, and also this initial data Q, they are both taken to be certain generalized stochastic processes. So we are now in general function theory, and also the stochastic processes that appear in our equations has to be general. and I specifically took them to be so-called Colombo general stochastic processes. Actually, in the papers that they are considering, where authors consider heat equation, fractional heat equation, the usual situation is that K is constant, and they usually consider the equation not on infinite domain but on some finite domain. Here we decided to take a more general case, so we take this thermal conductivity to be a function of both T and X, and we consider the equation on the infinite domain. And as I said, we took a derivative from the right-hand side to be so-called rate derivative. And the general stochastic process that appeared in the equation we take to be of Colombo type. I mean, there's no way that I can explain the Colombo theory during the half an hour or 50-minute talk, doesn't matter. It would take me some time, and but I will simply show you a few slides just to, as my professor would say, just to be scared when you see them, and nothing else. And then, yeah, I mean, it would take me an hour at least in order to explain everything in details. But for instance, it allows me to take, for instance, generalized white noise process as a stochastic process that appear in the equation, because one can show that every stochastic process can be represented in the form can be viewed as a Colombo stochastic process, because you have an embedding and everything that it should be. Okay, so basically this P and Q that appears in the equation from the last slide, here it is, they are practically arbitrary. They could be practically arbitrary Colombo generalized stochastic process. The thing that is important here that they have certain growth, because if we could control it, then that everything stays where we want to stay in this our theory. Okay, as I told previously, we will use this fractional derivative, and we will establish and prove the result, the existence and uniqueness result within our Colombo space, and we will use the theory of uniformly continuous, generalized again, uniformly continuous semigroup of operators. Okay, and as I mentioned at the beginning, the first thing that we do is that we write our equation. So now I decided to show you how our theory works in this, on the example of this heat equation. And first we write it in the operator form. So we write it in the way that from the right-hand side we have operator A alpha, where A alpha is given with this thermal conductivity times this fractional derivative. And as I said, instead of this original problem, we will solve an approximate problem. I will show you later how we obtain this approximate operator A alpha tilde. And we actually obtain it by simply by regularization of the derivative that we obtained. And we prove that A alpha and A alpha tilde are associated, and in that, in some sense, that approves our approach. So the problems that we are considering, both problems, the original one and the approximate problem, are associated. They are not too far away from each other. Okay, and few words about fractional derivatives. You see so many terms here just in order to start solving the problem. Okay, this is the definition of the left fractional derivative of order alpha. Pay attention that alpha here is between m minus 1 and m, where m is an integer. And since it is left, so this integral goes from minus infinity up to x. And you see the definition. If alpha is equal to n, then it coincides with the usual integer or the derivative of order n. And again, the theory shows us that this definition can be extended to continuous linear map from fractional Sobolev space H alpha into L2, and we denote that extension of the fractional derivative by this, you see, this, sorry again, this D is not italic, and here we use this italic notion, so this is that extension, and we actually use with that. We work with that derivative. One can do the same with the right derivative. You see the differences. Here we go, we use the integral from x to infinity. Okay, and again, one can extend the definition to continuous linear mapping and use this extension. Okay, and finally, as I mentioned, that we will work with Riesz fractional derivatives. The Riesz fractional derivative can be obtained, can be defined by using left and right alpha fractional derivatives, as it is written on the slide. And one can show the Fourier transform of the since you needed that the Fourier transform of alpha Riesz fractional derivative is given like on the slide. And why this Riesz fractional derivative is interesting, because somehow it represents fractional Laplacian. Okay, and now, as I said, a few slides to scare you about Colombo spaces. The whole idea about these Colombo spaces is to work within the spaces where you can multiply any two generalized functions. So if you have two Colombo generalized functions, you can multiply them all the time, every time, not like in the Schwarz distribution space where multiplication is not well defined. So the first thing that you do, for the moment, you don't pay attention, you should not pay attention to these spaces, because they come from the problem that we consider, and it is not something that is very important. We can change those spaces here. But the important thing is that first you define so-called space of moderate function. Moderate in a way that those are functions with the following property, that for every t greater than 0, there exists c greater than 0 and n from n, such that this is satisfied. And all functions g that satisfy this condition, for all functions g, we say that they have moderate bounds. So first, we define so-called space of moderate function. Then we define space of negligible function. The definitions are, let's say, similar, but instead of here in the previous definition, we say there exists. C, here we ask that to be satisfied for all. Where is the definition? Sorry. Yeah, for every, yes, sorry. For every A from R. You see, here is, there was exist n, and here is for every n. And for such function g that satisfy this condition, we say that they are of negligible type, or that they have n bound. So one can show that both spaces of moderate function and negligible functions are algebras, and the other space of negligible function is an ideal of the space of moderate functions. So therefore, you can define the factor algebra of these two algebras. And this vector algebra is actually called the algebra of Colombo generalized function. So sorry, but that is the main idea. I will skip all the other slides about my Colombo spaces that I will use here, and I will simply mention to you that, of course, I need to introduce the Colombo version of stochastic process. So I do the same with the generalized stochastic process that appear. I do the Colombo generalization, and it can be done in a similar way. So I'll skip it too. And I finally come to the part where I want to say a few words about uniformly continuous semigroups, which I will generalize to later. So this is the usual story about uniformly continuous semigroup of operators. I mean, they are basically it is a right derivative, and x is from D of A, and D of A is actually the set like this, and it is the domain of the operator A. So this is classical theory, and this is still classical theory if the semigroup of linear bounded operator satisfies this condition, then it is called uniformly continuous. And it is known that linear operator A is an infinitesimal generator of uniformly continuous semigroup if and only if A is bounded. So this is classical theory, and then in that case, I mean every uniformly continuous semigroup of operator has the unique generator, and this is the connection. This is how you write semigroup of operator by using generator. Okay, and now we generalize the whole story. I will not show you that, but the whole idea is that we introduced again the space, the appropriate space of Colombo functions for semigroups and for this infinitesimal generator, and we define spaces which our objects are. So we will skip it. And okay, so all the I prepare all these slides just in case if someone has some particular question. I don't know whether somebody here is familiar with the story, so then I can go back and show to that person if he or she wants to know something more. But I plan to skip it. So all this story is about the generalization of theory of semigroup of operator. And I'm almost done. I will briefly say something about finally about the equation. So first of all, in order to solve our equation, this heat equation, we need our operator A to be of certain growth. So we call it H epsilon type, and as you can see, it has to be satisfied something like this. now I will go to the main theorem because, sorry, still I have to say this. You remember that I said that instead of original problem, I consider the approximate problem. How do I make this approximation? By simply regularizing the derivative that appears in A. And how do I do this regularization? Simply by the convolution, this convolution by a certain type of modifier. And this is usual idea how to do that in general extension spaces. And finally, if we go back to our heat equation, you remember that we had function f and function sigma. And both function f and function sigma should satisfy conditions written here. So we call it, if these conditions are satisfied, we said that f is of bounded type, and I will not read these four properties that should be satisfied, but if they are, then f is of bounded type. And finally, the theorem, the main theorem, is says something like this, that if our function f and function sigma that appears, sigma is something that is a function that multiplies generalized noise. If both those functions and their partial derivatives with respect to u and x are of bounded type, and that is something that we suppose, and if our both generalized processes are from suitable spaces and are of suitable type, logarithmic type, and if we suppose that we regularize our derivative in the way as we explained earlier, again with a suitable modifier, then we can claim that for every, okay, alpha is the order of derivative, there exists a unique generalized solution of our problem. And it is given by the usual formula that is often used for moderate solution when you solve the problems like this. So yeah, and too many conditions that we suppose in order to solve the equation, but I mean, we consider equation that could not be solved classically anyway, that can be solved numerically or by some other tool, so we are happy with anything that we get. And finally, as I promised to you, we prove under some conditions, which I will not read, that our two operators, original one and approximate one, are L2 associated in the, which means something like this. We show that this tends to zero, this norm. And as I told you, in many cases that we have considered, we also have the association of solutions, but I did not write it here because we don't have it for all the cases that we have considered, so thank you.
Some general ideas were cleared without details. So if you have some comments and questions, I said we had some group of people that working in this area and also in Novi.
I mean, when I participate some conferences where people were specialists, then it goes quickly because they are all familiar with all definitions and everything is quicker. But now I know that it's not possible to do it here. But thank you anyway for
some questions. Thank you again.
So first I would like